हेलो। So where is Professor Abhi? Oh, here he is. Yeah. I was looking for him. I was looking for you. So good morning, everybody. So this is the first set of workshops for FSCTCS 2023. And the first workshop is going to be Sat+SMT. And so we have our registrar, Professor Rajan, who's going to say a couple of things. And they have been kind enough to support us through the process.
That's part of hosting, right? Okay, good morning and welcome to Triple IT. So I think, well, the conference starts and the school is on for the next couple of days. But the most important or interesting thing for us is this also happens to be our 25th year. And this month is interestingly a month where Triple IT is hosting almost like 12 events in December. And about 3, 4 of them are international conferences, workshops, and winter schools and things like that. Okay, so we are happy to see a large number of researchers from across the country and also from abroad who kind of are actively participating in many of these events across the whole month on the campus, right? So it keeps our campus far more vibrant, not just because our students have a vacation break, but the researchers are still on campus, and I think they have a good time to interact with most of you and possibly benefit from the kind of knowledge exchange that will happen during these periods. Okay, so uh, I mean, go ahead, have not just your technical time, but also spend some time on the campus. Maybe a good walk around this place can help you. The long hours that you might be sitting in the room might give you a nice change if you go around the campus, have a quick walk and come back and stuff like that, right? But most importantly, please enjoy your stay here and welcome once again and have a nice and a wonderful workshop. Okay, goodbye. Yeah.
And yeah. Okay, so hi everyone. My name is Madhukar, and I'm one of the organizers of the Sat+Smt school this year. And so just a couple of announcements before we begin. So there are so you have Wi-Fi access, and the credentials are pasted at a few places here and there. So you should maybe take a picture and yeah, and there are washrooms on. I mean, there's one on the building right in front. There are some behind. You know, when you exit this door and on the other side of this of this hall, and there are a few in the next building here. I think there'll be markers which will tell you the directions. There are also a couple of rooms on behind this hall which are available for us. You know, in case you want to have a discussion. There's also a lounge which is so H103 and 104, I believe, are available to us for our use, which are right behind this. So when you exit from that door, you'll be able to see these rooms and so on. Okay, yeah. So I think with this, let's get started with the first talk of the day. So we have Ashutosh Gupta from IIT Bombay who will be who will be giving the first session. This will be an introductory session on Sat+Smt solving. And Ashutosh, of course, he's a faculty member at IIT Bombay, as I may have told, and he has been associated with this school right from the beginning. I think this is in the first edition when we had it in 2016 or yeah, something like that. So he's been associated with this school right from the beginning, and we are happy to have him here give the first talk. Yeah.
Okay. Hi.
You need this?
No, I have. Can you project the? Yeah. Okay. Hi. So I'm going to discuss what is SAT solving, and mostly it is directed towards someone who have maybe no background in this, and the goal is to get you a bearing. Okay. I may go to some technical details at the end of the talk, maybe after half an hour. So if you have any question, confusion, please ask. And if you find it's too less technical, I'm sorry for that. Okay. But let's see for 15, 20 minutes. Maybe we'll get technical. Okay. It's my own standard, what is technical. Okay. So let's start with solving this puzzle. Okay. How many have you seen of you has seen this puzzle before? Have you seen anyone has seen this puzzle before? The puzzle is simple. There are two white knights and two black knights, and you have to swap their positions. Any ideas? How would you do that? Like, tell me, what do I do? Move 6 to 8. 6 to 8? Can you go 1 to 8? Right, 1 to 8. 1 to 8 and 6 to 1. Now? No, swap all of both of them. Yeah, okay, go ahead. Okay. Any estimates how many steps it will take you to get it solved? It is impossible. Of course, it is possible. Of course. That's why would I? Otherwise, not a fun thing to do. Okay. So, so the first thing to see is that you cannot go out of this grid. Yeah, that's the logic. That's the problem actually. Okay. So let's suppose you think now you take a instead of puzzle solver, think a computer scientist had. How would you solve this? Like what if you have a computer at your hand, what do you do? Yes, search on what? All possible states. So what is a state? How would you describe a state? The position of 4 knights. So it's a vector of 4 numbers. And then you draw a graph. So how many possible states are there? What? Yes. So it's reasonably large. Not very large, not so large that computers cannot do it, but still large. Let me show you how would I solve it. Okay. Let's turn this into a graph. Okay. And this is a graph I'm going to draw. The idea is this cannot be seen. Okay, so let me use another color. Yeah, this is something rubbing against me. Oh, that thing. Oh, yes. Thank you very much. Yeah. Okay. Yeah, let me use the black color. Okay, so let's look at this position 1. From where can you go from position 1? From position 1, you can go to 8 or 6. So I draw an edge, 8, 6. Okay, position 2, where can you go? Yeah. I'll come to it. Yeah, just first let's draw the graph. Okay. Now 7 and 9. Okay, 2, 7, and 9. Okay. And let's go to 3. If you go to 3, we can go to 8. 3, I can go to 8. And 4. So from 3, I can go to 8. And is there anywhere else? No. Right. So 3 is something interesting. Right. You can, if you get 3, the only way to get 3 is from 8. Okay. So please remember that. Okay. Now 4. From 4, 5, and 9. 5 and 9. So 5 and 9. Okay. Right. 5. From 5, 4. That's it. 5 is another dead end. Okay. So 6. From 6, where can I go? 10 and 1. 10 and 1. And can you anywhere else? 6, 10, and 1. Right. Let's go to 7. Where can I go to 7? Okay. From 7, 2 and 8. 2 and 8. From 7, 2 and 8. Right. 8 is special. Do you see something special about 8? 8 is another specialty. It has 3 incoming edges. Okay. Something interesting to see. Okay. 8 and 9. Are we done with 9? 9 is 2 and 4. And 10, 6 and no. Okay. So you draw this graph. Okay. Let me draw this graph in a much more interesting way. Okay. You don't see anything here, right? You see, you don't get any insight. Now let me redraw this graph and you will see it immediately the solution. Okay. It will hit you like a lightning. Okay. 3. Okay. From 3, I can go to 8. From 8, I have two places to go. And let me not start from 3. Let me start with 5. Okay. Let me start with 5. 4. From 4, I go to 9. 9, I can go to 2. 2 to go to 7. 7, I can go to 8. So 7 to, sorry, 8. Okay, 7, I can go to 8. 8 to go to 3. Let me draw 3 like this. And 8 can go to 1 and 6. And where are these guys sitting originally? They are sitting at 3, 1. So black guys are sitting here. And white guys are sitting in 6 and 10. 6 and 10. 6 and 10. I forgot to write 10. Where is 10? Okay. 6. Oh, yeah. 6 goes to 10. Okay. Now you see the solution. What is so special about 8? That's a parking spot. Sorry, 3. 3 is a special. It is a parking spot. It's a traffic jam between these two. So the blacks are on one side, whites are on the other side. They have to cross each other. Okay. And how would you do it? Just use 3 as a parking spot. Move the black all the way on this side, bring the white guys in, black. Do you see the solution? Okay. Now the question is how many steps it will take. I hope by the end you will know. So, so you can see that what it has to do with SAT solving. So the thing is, problem was presented to you somewhere. You modeled it in this way, right? Right? And the way it was drawn, there was no insight. You couldn't understand what's going on. But when it presented in a proper way, you had the solution immediately. You could see it. That's the issue of if anybody wants to solve a hard problem. A hard problem like SAT solving will be presented in a set of constraints. You want to solve it. If you draw them as some sort of constraint form, it will be a spaghetti. You will not understand anything. And SAT solver's job is to find this insight on its own. No human intervention on its own. It learns clauses and a lot of machinery it has. But all that machinery's purpose is to find this insight. Maybe there is no such insight. Sometimes it's not there. It's just problem is just hard. There is no way. Okay. Then SAT solver can't do much. Maybe it can do. One day somebody will discover it. But so far, whatever our techniques are, have limitation of finding these insights. Okay. So the 3 steps involved here are presentation of the problem. It will given to you by some user. Okay. Modeling and insight. Okay. Any algorithm related to SAT solving is finding that insight. And they call it clause learning, all sorts of name that you will hear. But they all follow this basic pattern. Okay, I hope that is clear. Okay, so so before going to SAT solving, let me spend about 15-20 minutes try to think about what is so different from what are we doing here. Okay, what is the high level goal here? There are hard problems that needed to be solved. Okay, and theorists have told them these are the hard problems. Computers will have a tough time solving them. And practitioners have already implemented all easy stuff, the Google, etc., Facebook. Okay. Now we are asking the question, can we solve the hard problems? First thing, what are those hard problems? Do we need to solve them? And what are those techniques? Okay. So theorists have already told us they are hard. So there is no way there's no magic out there in the world. There will be time you will be stuck. You will not be able to solve it. But still, we solve them. We will see a few examples. And we will see why do we need to solve them and what people actually do to solve them. Okay. And what computer scientists have been trying to do to solve them. Okay. So this is you know what this saying is? Sam Dam Dand Ved. What does it mean? Excuse me? No, the Hindi one is much more nuanced. It has 4 steps to attack a problem. It has 4 words. It means 4 different things. Can anyone explain me what Sam Dam Dand Ved means? It's Sanskrit. Okay. I think it's Sanskrit. Yeah. Yeah. Blackmail. So there are 4 ways of getting things done. Normal way, bribery. Third is basically punishment. Fourth is blackmail. And you must do things in this order. That's what it says. It means, yeah. Bhed means divide. Bhed also means secret. In Bhed is this. Oh, this comes from divide. Oh, thanks for. I don't know. Okay, I didn't know. Sorry. Okay, Bhed has 2 meanings, right? Yeah. Okay. Thanks. Okay. Anyways, so I thought ki this is basically any which way you can solve the problem. There is no principle here. Okay. First of all, you have to understand no principles here. All I want to know is it SAT formula. Whatever problem I had, I want to solve it. Whatever I can do. Okay. So computer solves many problems, business processes, search, weather prediction. And we have these problems which we have been solving with computers. Okay. So some are easy, some are hard, some are impossible. So theorists have already told us. I'm not going to use formal names. Okay. So I'm completely, and even if I use them, probably I'm doing them wrong because I don't remember a complexity theory. Okay. So from that point of view, I approach things. Okay. So I really don't care about complexity theory personally. Okay. All interesting problems are hard for me. Has to be hard. Okay. So they're easy, hard, and impossible, right? So so easy example is best way to go one place to another. Let's say how to Bandra is a place in Mumbai, but let's say I don't know what places are in Hyderabad, but let's suppose how to get to Delhi. Okay. So this is shortest path problem. People have studied it. Google can does it very efficiently for you. So it is sort of, you can classify it easy. With hard problem, you can say play chess. Chess is already beaten. Maybe you can think of playing Go and etc. So these are hard problems, and there are impossible problems. And theorists have told us they are just impossible. You cannot solve them. For example, program correctness. In next 1 minute, will my program crash or not? Sorry, my phone will crash or not. If you want to predict that result, that possibility, it's impossible problem. Okay, it's classified as impossible. It's program correctness it's impossible. Okay, but we don't give up as a computer scientist. And first, let's try to attack hard, and then you'll see that we are also working on impossible problems, and we have made a big dent in this space. Okay, so let's see what are the hard problems. Okay, so let me give you the first example: scheduling. What is a scheduling problem? What were you doing here? Like there's a schedule. This time my talk will happen, and you are here. Okay, this is scheduling. What happens when? Okay, so you have several people who wants to attend various talks. People who are giving the talks, there are rooms, they have constraints, and you have to put them in a different place. Okay, this is a scheduling problem. It's considered a hard problem. Okay, if you ask a theorist, they say yes, it's a hard problem, but it is being solved everywhere. Planes are flying, classes are happening, you are here. So how did we solve this if it is a hard problem? Did we run a SAT solver? No. So what happens in the real world when you confronted with a hard problem? What do you do? How was it solved? Was it solved? Actually, that's the question. What actually happened? Can you have a view on it? Approximately solved. You ignore certain constraints. Some people could not have come here. Okay. We said, okay, you can't come here, scheduling conflict, don't show up. Okay. The other thing is provide extra resources. For example, you are allocating, even if the class, your institution can run with the 20 rooms, they may have built 30 rooms. Okay. If you provide enough resource, scheduling problem becomes actually easy problem. Okay. So for them, building an extra building is cheaper than running a SAT solve. Think about it. Okay. So so that's what they do. Okay. And I mean, in flights, there's a conflict, you just cancel the flight. Okay. So There are many, many important things. For example, your phone. Today, you carry a phone around. 20 years back, this was not possible because circuits were just too hot to pack in a phone in your pocket. Now they're there just because we're now able to optimize them so well, then they don't get hot when you watch a video. Okay. And that's why this technology is possible. And because somebody solved a hard problem. Okay. Like playing chess, you know, all that. For example, protein folding. Okay, it's a very, very important problem. Actually, it's the problem of the time. You predict a given DNA sequence, how does it fold into a protein? Okay, there are a lot many more steps. I'm just simplifying too much. Okay, and so there is some significant improvement there also, AlphaFold, for example. So the people are trying to solve these problems. Okay, and because of we can't predict protein behavior, we have had a long time actually producing a vaccine for COVID-19. One of the many problems to producing vaccine fast is one of the problem is how to do protein prediction or protein folding. Okay. Okay. So again, there are two subclasses. I have to make this. Let's make it very clear. This is non-deterministic NP complete and sorry NP problems in which you, if I give you the solution, you know it's correct answer. Okay. So if I give you a password, you know, and you can just type the password in the system, you know it's a correct password, right? So once I give you the answer, you know it's correct. Okay. Right. So scheduling, if you have made the schedule, then it works. Everybody is satisfied. You know that's a correct schedule. Okay. Okay. And SAT is an abstract version of all these problems. Okay. So we will come to that. Okay. Okay. So there are problems which are classified as hard, but not impossible, where even if I give you the solution, you can't tell me. Okay. For example, protein folding. So even if I give you a protein folding, you don't know it's actually the reality that happens on real protein. Why? Because you don't know it's actually a minimum energy configuration. There may be another minimum energy configuration. In the local neighborhood, may be able to prove it, but you don't know that all possible configuration of this protein, this is the minimum energy. Okay. So even if I give you a guess, oh, this is my guess to the answer of this problem, or even if I give you the real solution, you wouldn't, it will be very hard for you to be convinced. Okay. Until you build a microscope which is big enough and actually see. Okay. And seeing it's a known problem. What do you mean by seeing something? Okay, because these proteins are constantly fluctuating. You don't really see the real thing if you ever see them. Okay. Right. So so this is the just understanding what the hard and easy problems are. They are everywhere, important, and need solving. Okay. So how do we solve them? Okay. So just a side comment, there are impossible problems. For example, correctness of programs. This is considered a impossible problem. Okay, let's not dwell over that too much. Okay, so what do we do to solve them? Okay, so I had said Sam, Dam, Dand, Bhed. So let me classify 4 ways. You just design a normal way. You basically design clever algorithm as good as possible. And that's what you do in a data structure courses. Shortest path, minimum spanning tree, you must have done all that. And try to see if you can solve them in that way. If you can't, you still doesn't work, then you basically, you apply brute force. You buy thousands, tens of thousand machines and try to just, run an expensive algorithm on those huge number of machines. Sometimes it does work. Okay, so it's not the case that it is impossible sometimes to break that. I have solved some problems for industry in which just brute force worked. Okay, nothing else worked. Okay. Right, done. Basically, you try to basically cheat, okay? Punish the problem by heuristics. You try to guess. Maybe if I make that guess, it will get solved. It does happen, okay? And that's the mostly what the SAT solvers do, okay? They come up with various heuristics and try to break into the problem without really knowing how it could have been possibly happen, okay? So, so you will see today by Clark's talk, how the SMT solvers are doing this, okay? And as I said, is that Bhed finally is you just, which I meant actually blackmail, okay? Basically, you do approximate solving. You do not actually really solve the problem. For example, AlphaFold. Do you know what is AlphaFold? It predicts the Google's program. If you give it a protein sequence, DNA sequence, it predicts the structure. Okay, it is beating everything, like so far anything other researchers have done. And but at the end of the day, if you look at what AlphaFold does, it is basically says this is the folding, take it or leave it. Okay, because there's no other way of checking it as it is. What people are doing is right now to check it, look at the folding, how it looks like, get the shape of the protein. You can image the shape of the proteins now. So you see that it looks like the image looks like that or not. Okay, so there has been some confirmations actually. So that the what AlphaFold predicted, and actually that was found. Okay, so but it has been widely wrong also. Okay, so this is again, it's a very very crude way, I mean wrong word. Okay, some way of solving the problem. And we are humans, we are confronted with this reality, is a human reality. We have a hard problems, we will try everything. We have no principles. Okay, AI works, we will do AI. If we can do heuristics, we do heuristics. Because it's our reality, we need to solve this problem. Okay. 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 So let's study what is another aspect of the problem, resource limitation. Okay. How much computation can you do per second using one machine? It's just usually your laptop. In what order? How many operations can you do per second? 10 to the power 9. Okay. Yeah, you have been in my class, I think. Okay. 9. Okay. Let's suppose a reasonable lab. How much time do you have to solve a problem? Just a rough number. What? Let's say week. Okay. Let's say week you have a problem. 10 to the power, let's say 10 to the power 5 seconds. Okay. I don't know where this number coming from, but like maybe a day or two. Okay. Maybe a week. Okay. 10 to the power 5 seconds. Okay. How many computers can you possibly buy? Okay, imagine like you entire city, Mumbai city buys laptop computers. How much? Like, what do you think a reasonable lab? 10 to power, yeah, 10. It's actually very good guess. Actually, 10. I put 10 to the power 5. 10 to the power 5 is I can imagine someone can, a reasonable lab can buy. And the 10 to the power 7 is actually is not, is realistic. If you have a company, a large data center, yes, this is realistic. So you see that if you multiply these numbers, you get about 19, maybe 20, maybe 22. This is your hard limit. You can't cross this line. Any computation you do has to fit in there. Any intelligent, no matter what algorithm you invent, has to fit in this like, it's like hard constraint. You are hitting the nature. Okay. These numbers may change over time, 10 to the power 9 become 10 to the power 10, but it will not dramatically become 10 to the power 100. And there are problems which need 10 to the power 100. Okay. And they are there in around us. We need to solve them. We go talk to industry, they will tell you, this I need to be solved. Okay, I need to solve, and I need you to solve this. But you need to fit into the power 20. Okay. And that is the another thing you need to think hard about. Okay, there's no, if somebody say computation is infinite, oh, it's cheap. No, we already have problems, cannot fit in all the computers you have in the planet. Okay, so yeah, so that's there. Okay, so there's another dimension to entire discussion. Okay, you know what is two body problem in physics? Yeah, two masses. Yeah. So they follow elliptical paths, right? So it's a two body problem. Can you solve it? Can you give the closed form? Yes. Can you solve three body problem? You cannot. Okay, right? There is no answer. Now the question is, can you solve 10 to the power 23 body problem? Yes, that's you. You can predict your hand will be, and it's a 10 to the power 23 body problem in that scale. You see what I'm saying? So how could you predict the position of your hand, but you could not predict the position of three bodies? What happened here? Yeah, so the thing is, in 10^23 body problem, you are predicting not exact position of every atom on your body. You have other kind of claims that, you know, it's hot, it's cold, it's approximate position of my hand, okay? And mostly it is the realm of the statistical physics. Okay, so you switched from a combinatorial world to a statistical world. Okay, so this stable behavior of this projector, this is all statistical, and this is combinatorial, the three-body problem. Okay, so in computer science we deal with combinatorics. Okay, but there's some point of time it switch over to statistical world, and then it start predicting again. Okay, now we have a lot of problems which are in this space. Okay, mid-size problem. How many proteins you have? 10,000, not a billion, not about 3. Okay, how many copies of the proteins you have, the DNA you have? 2. Okay, maybe 1 actually. Okay, so the numbers are finite, and then you go into this space where you have to remain combinatorial. You cannot switch over to statistical. For example, if you do chemical analysis, the big assumption is there is a diffusion which is ready to use. Okay, diffusion means every molecule is everywhere, can go anywhere physically, but that's not the real world. In a cell, in biology, molecules have to move from one place to another, and when you go from one place to another, nobody should touch them. Okay, right? So all those things are very difficult to model. So you realize that this place where things are still combinatorial, but cannot be do statistical, but numbers are large enough, is unsolved domain. We do not have any solution there. Okay, so that's where we are. So what am in terms of time, where am I? Okay, 10, 11. Okay, I have 20 minutes. Okay, right. Okay, so let's get to the graph coloring. Okay, so let me take one example and do something interesting. I mean, I said earlier, I will be very non-technical so far. So now it switches over to technical. Okay, let's take one such hard problem. The idea is you have a graph and a set of colors. Assign a color to each node such that no edge has same color in both ends. Okay, this is a standard problem. Okay, so for example, this is a graph which is colored using 3 nodes. Okay, and red, blue, and green, and each one is given one color. Okay, do you agree this is a correct coloring? You take 3 edges, each edge has both ends have a different color. Okay, can we color this thing using 2 colors? Cannot, right? So no matter, I mean, just ignore, you cannot, if one is red, other is green, third node cannot be red or green. It has to be choose something else. Okay, right. So can we color the following in three colors? Yes, you can. Okay, so it's like the same red, blue, green, and the one you choose one of those which are not used in the center node. Okay, so I hope this is clear. Okay, so we will see the solver. So how do you solve this problem? Okay, so what do? We build a constraint. Okay, so we'll come to the solver first. Let me show the constraint, then we will run the solver. Okay, so we make Boolean constraints. Call a solver to solve the constraints, and solvers which we use are called Sat solvers. Okay, so let's see how what Boolean constraints are. Okay, so let's look at formally the definition. Let's suppose Vn to Vn are the number of nodes. They have set of edges, and we have D colors. Okay, and each edge is Vi comma Vj. Okay, and then you color is such that color of Vi and Vj are different. Okay, so it's written the same definition written in a formal way. Okay. Okay, so what are my variables? So first, when you try to solve a problem, you do modeling. Remember that I had a problem, I had a model, I had an insight. So I need to go to the modeling step. So the modeling, what will happen is that I will assign every node and a color pair a variable bit. Okay, Pij. Pij means ith node. If it's true, ith node has a jth color. As simple as that. Okay, right? Pij is true if and only if Vi is assigned jth color. Okay, that's the statement. So first constraints I will add is that everybody gets at least one color. Well, ith node must get at least one color. So one of those bits, PI1, PI2, PI3, PI4 to PID, everybody should get at least one color. Okay, so this is one constraint. You need to say that. If you take an edge Vi and Vj, right, then this must not have same color. So just say if you connect the edge, if Pij is true, Pi if Pik is true, then you cannot have Pjk also true. Both cannot be true at the same time. Okay. Take their conjunction and the entire thing should be false if you negate it. So this is a disjunction of, right? Pik means kth, the node I has not been assigned the color k. So it has been assigned color. So not means has not been assigned. So either kth color is not with I or not with j. Then it's okay, right? And I'm saying I'm done. Is there something else I need to add? Yes, yeah, you have seen this in a class. Okay, yeah. So you have at most one also need to be added, but it is technically not needed. Let's not do. If you want to solve the, think about it. It's not needed. Okay. So let's try to see a solver. Okay. So here is a solver. It's a Python program. So I have a graph. Okay. So let me open this graph also to just show you. Okay, so this is a graph which has 500 nodes, and you have a sequence of pairs. So you will have a 57th node is connected to, is undirected, 261, it's undirected graph. So sequence of pairs, about 7,000 edges are there, randomly generated, okay? And right. So what do? You basically, I have 500 nodes. I declare I have 3 colors. Then I read my file, okay, and gives me set of edges. Then what I will do, I will run an experiment. I will try to color, assuming that I have 1100 edges only. Then I will solve it again with 1110, 1120, and I go up to 1300. It's just an experiment for this meeting. Okay, so just that's these parameters, we can play with it. So now I will build first variables. So I will create for every node and every color Pij, there is a variable. Okay, it's a Boolean variable. So in your this is importing a library Z3, and you can declare a Boolean variable there. Okay, so this is declares. Now what you can do, you can define a constraints for every node. For every node, I can define a constraints or of all bits. Okay, VSI means all the bits related to ith node. Okay, so this bit vector, this is a vector of vectors, right? Sorry, vector. Yeah. So Vi is a vector. You're saying that all the bits related to the color of that node, you take the OR of them. Okay, it is very compactly written using all Python gimmicks, so it will take some time to parse if you're not familiar with Python at all. So right, so this is a set of constraints for the nodes. Okay, then for you iterate over all the edges. Okay, right, the edges of my interest up to that limit which I want to analyze. Okay, and for every edge I add this constraint for every color. Okay, for every color I'm saying every color and every edge I am creating a constraint that the same color must not appear in both the nodes. It's just simple Boolean logic, nothing more than that. Okay, it's written with and not and not and or. Okay, sorry, or and not. So it's as simple as that. Okay, right, and then add these constraints in your constraint store. Okay, now here is a setup of the experiments. Okay, what will I do? This is my solving step. Okay, look at this. First I create the solver, I add all the node constraints, then I will consider some number of edge constraints, not all, some number, 1100 first, then 1110, then 1120, and so on and so forth. Okay, and measure the time. Okay, time measuring happens here. I start time, I measure, and then do the total time taken to run. Okay, and then I report my results. Okay, let's see how it works. Okay, so if I run my graph.py, to start solving. So 1100 it's solved in 0.07 seconds, then 1110, 0.08, then start slowing down, and 1150. And what do you think what will happen in 1160? Okay, so let it run. Okay, let me continue with my talk. Okay. Okay, so let me get back to satisfiability problem. How much time do I have? 15 minutes. Okay. So, so far I've been talking about more general problems. Now let me get to the satisfiability problem. What is a satisfiability problem? And I will not have time. How can it model everything we are talking about? But it will give you a sense what is a SAT problem. Yeah. Excuse me? Yeah, I'll come to that. I'll come to that. Let's first see what is happening. Oh, still stuck. Okay. Okay, that's interesting. Okay. So right. So let the solver do the job, then I will come to it. Okay. Right. So satisfaction. So what is the satisfaction? Okay, it doesn't have to be Boolean variables. It can be any kinds of variable. Let's suppose X, Y, we rational variables. And choose a value of X and Y such that formula holds true. Okay, so what is the value of X and Y? What do you think? 1 and 2. So this is a basic satisfaction problem. Okay, this is what we are doing. We're giving you a formula and give me a value. Okay, nothing more than that. Okay, now story gets complicated. Okay, of course, if it was so easy, then we would not be talking about it. So this object is called model, and this is a formula. So the question is f SAT? Basically, give me a model given a formula. So is this formula SAT? Right? Okay. Is this formula SAT? What? What do you say? SAT or SAT? Okay, it's not SAT. Is this SAT? Oh, yes or no? Yeah, but there's something more about it. Every X satisfies this. Right? It's called valid formulas. Okay, so let's see what solver is doing. If I hope my oh, it took 150 seconds. Okay, now I have a bet. What will happen for 1170? Time will go up or time will go down? Or how much up? What? What do you think? What will happen? You have to answer fast, otherwise may come back. What? Up? Okay. Okay, let's see. Okay, let it run. What is any I can have a betting. It's independent runs. Each time it's restarted. What? Not before this. Of course, it has to. This entire experiment has to finish in the next 20 minutes. So it will. What will happen? Okay. Right. Let's wait. Okay. Let me continue. So this is a valid formula. Okay. Okay. So again, let's look at our problem again. X plus. So we add y greater than or equal to 10. We solved it. Then we add one more constraint, become unsat, right? But be able to reason fast about it. Okay. So this is a one class of problem. Okay. Instead of adding conjunctively X greater than 0, I could have added this kind of clause, X greater than 0 or X less than or equal to minus. Is this SAT? Okay. So let me go back to the solver. Oh, 82 seconds. Time reduced. Now, next bet. 1180 edges. What will happen now? It will go further down or go back up? Who who is betting on reduce? And who's going to go back up? Oh, you were betting up. Okay. See. How much go down? Let's say numbers. It's more than 80 seconds. Oh, this is not real time. Presentation is running in the parallel. So much is happening. And you can see my hard disk is crashed. So you can see the hard disk stuck in the tape. Okay. So 75 seconds. It went down slightly. Okay. Okay. What about next one? And you know that it goes till 1300 only. So there's something will happen. Okay, soon. So what? Even down. Even smaller. Why? And how much smaller? 40 seconds. 40 seconds is one bet. Okay, another number, 40, 41, 42. 30 seconds. Anybody guesses? Okay, so let's continue with my presentation. Right. So there's another class. Then you can put a quantifier on it. Can say for all y this must be satisfied. Okay. Right. So you can say that first layer is only conjunctions. Then you have a disjunction in it. And then third layer is you introduce quantifiers. Okay. And there are real world problems which match to all these three. Okay. So is this SAT for all y? Yeah, for all is for whole thing. Yeah, sorry for the notational issue, but yeah. Okay. So so they have names. These are, first thing is called theory formulas. Second class is called quantifier free formulas, and third is called quantified formulas. Okay. And this is, first one is roughly called easy. It's not easy, but roughly called easy. Second is hard. I'm not using technical names and considered very hard. Okay. And of course, we are attacking the third layer also. So in our community, people are trying to solve quantified formulas. Oh, same amount of time. It didn't go down. It actually slightly went up. Okay. It's because other things are running actually. This is not I was expecting actually. What? Excuse me? Yes, it went to 45. Yeah. 35. So why it is coming down? That is actually the interesting bit. That's what I want you to think about. And that was the insight. It goes to the insight point. Yeah. So many edges. So yeah. Easier to detect the contradictions. Okay. That's the main point. Okay. So the thing is so that is the correctly stated, is that initially the first time the contradiction arrived, it was a very long ranging contradiction. You color this part, that part, and then you get a contradiction. Then you go back and you color again, and then you back and try. This all will be explained to you by Clark, how actually it happens. My job is just to give you a glimpse. Okay. So let's see, time is reducing constantly. It is not going back up again. Okay. And so now 8 seconds. Okay. So the point is that if you have a more constant, if you have a random graph with sufficient density, very high probability you have a cliques. Very high probability that you have a four node cliques. Okay. And if you have sufficiently many edges and it's a randomly generated graph, okay, first of all, it's a random graph. Random graph is not the real graph. Reality is different. Okay. So it's a random graph. Oh, yes. So this is the graph I was looking for. Okay. So you can see that around 1150, it spiked. And at this very point, the transition from true to false happened also. So that is anything interesting to note. And then time went down constantly. And then by the end, it is actually as if problem was easy. Okay. So here, the idea is clear, right? If you have a long range reasoning, then it's, of course, your life is tough. But once you are sufficiently constrained, you're able to find cliques. That is the SAT solver's insight. It's looking for those cliques. If it finds them fast, it says one SAT. Okay. How from this sequence of clauses, it detected, say he has to find the cliques. That's the magic of SAT solver. And apparently it is agnostic to the problem type. It just, you give any problem, it will detect. Okay, they have an abstract idea of learned clauses, and that basically capture the idea of cliques and whatever your problem may have, the insight you are looking for. Okay. Excuse me. Excuse me. Yeah, but it's doing it. Okay. But there are times when it doesn't. Okay. Now I'm lying you in two possible ways. In this graph, I have two lies. What are these two lies? One lie is it's unnecessary zoomed out. Remember, I started with 1100 and ended at 1300. And how did I choose these two numbers? Okay. I should have started with 0 and 10, 10, 10, 10, 10. And I have 7,000 edges all the way. So actually, if you plot the entire thing, the graph looks like just a spike in the middle. So if I give you an arbitrary graph connect problem, let's suppose, most likely you are here or there. What are the chances you will land up right there? Okay. And that is the magic of SAT solvers. Nobody has a proof for it. And of course, you're welcome to, nobody has a proof that the real world problems have this property that you land up here or there. Okay. And this is one of the open questions. And if somebody cracks it, it will be most famous person. Okay. But that is what is happening. There's another lie here. What? Number of edges. Yeah, yeah. Number of edges. Yeah, yeah. Most, listen, what will happen? The spike, the spiky part will be larger, but most of the problems will be easier. Okay, right? One more lie. Choice of the graph. Okay, I chose the graph. So I generated many random graphs and see which was the worst spike. And I'm presenting you that one. Okay, right? If you generate many random graphs, you will find very few graphs have this is such a sharp spike. Most graphs will have very small bump. Okay, so so when a fact is presented to you, be very skeptical, doubt, where did you get this graph from? Okay, that's the question you should ask. Okay, so I deliberately lying to you by showing you a graph in which Z3, a specific solver, performs worse than a specific version of it. And I have tested with other version, and it does get better. So I stick to that particular checkout version to just do this drama. Okay. So okay, so this is the message with this plot. If you have any question, please ask. Okay. Okay, so the basic ideas: quantify free formulas. Okay, so you have theory atoms, you have a Boolean structure. So for example, you have these theory atoms which are x plus y equals to 3. Yeah, yeah. Yes.
Hello.
Yes, so SAT solvers are mostly designed to, actually what they are doing is trying to get the satisfying assignment. Okay, so if this is unsat problem, it has to really prove that all possible assignments are not going to work. So it will not necessarily be the worst, but it is basically takes more time to really show that is unsat. It's better off to live with the SAT problems. Yeah. Okay. Okay. No, it's not. I mean, it's depend. I mean, there's so much going on. I mean, you see, the point is sometimes unsat insight is so trivial. Once it's unsat, it's very easy to say. There are theorems where very easy to argue why in this situation you cannot have a real solution, but actually finding a solution can be very hard. Okay, so there are like non-constructive proofs of the theorems. For example, if I give you two irrational numbers, are there two irrational numbers? Let's say P and Q. p to the power q is a rational number? Are there such p and q? The proof of this is non-constructive. It gives you that yes, such pairs exist, but it doesn't give you the pair. Okay, if you want interested in proof, I can do it after the talk. Okay, it's a very short proof, and you'll scratch your head at the end. Yes, it didn't give me. So it is possible that sometimes SAT it's different than things change in very dramatic way. It's very hard to say that the clean statement cannot be made. Okay. Okay, so yeah, yeah. I don't know. I have not tested it, but yeah, this is a good point. Yeah. So yeah. No, I don't know. Okay, I think my time is up. So what is my time? Can't bore you anymore further. So yeah, so let's end the talk here. I think it's a reasonable point. Yeah. So any questions? Yeah. I hope you are enough excited to learn about SAT solvers now. Okay. Thank you. Okay.
You ask.
Just a quick, it is just a clarification. So the point, the example about you're taking a particular graph and then you're adding edges and then you're plotting, at what number of edges there is a switch from being satisfiable to for the SAT clauses to be satisfiable to to unsatisfiable. But I missed that particular point about the choice of the graph to begin with.
So how did I come up with the graph I'm presenting to you? So what happened is I came up with this idea. I will do this experiment in the class. So I said, okay, let me generate random graphs. Most of the graphs, what happens is there's no spike. Okay, and very few graphs have a spikes and very small one. Okay, you can do it yourself also. I just give you the code and try to generate random graphs. I have a generator. Okay, and once a while you find a graph which is a huge spike, and that too. Yeah, I'm just showing you that. Okay.
So the graphs that you're saying, the spike is like this plot, right? So you're
Yeah.
saying that you start with a graph and then you add edges to it, and then you get this plot.
Yes,
So you're
yes.
saying the choice of the graph to start with, to which to add edges,
Yeah.
depending on that, you will get your.
Yeah,
Okay.
yeah. Yeah, you will not see anything. You will just set to unsat transition. There's no effect. Okay. This lot theoretical stuff is out there. You can take my next course, CS433. Okay.
So
Yeah.
Ajit, you said that there is one has to, given a problem, you have to, the next step is to model it. And when you modeled this particular problem, you introduced variables which said that this is the color that will assign to this edges.
Yeah.
So there is a lot of effort that I think goes into. So how does one decide that I'll need these kind of variables?
It's human to decide what the model is. Okay. And it depends choice of model. For example, I didn't add at most one. Okay. It's my choice. I could have added that constraint. So the human made a choice. Choosing this variable, that's where we see a SAT business can look in future. If some SAT solving company trying to do a business, they will say, okay, I will take your problem and model it efficiently, which works on a specific solver. If you go do it naively, it won't work. Okay. So yes, even if very simple problems, you have choices. For example, this one, if you have anything realistic problem, you have so much room to play with modeling. Okay. And especially you can see the latest work by Martin Hewlett, right? Am I pronouncing what? Okay. I'm bad at pronunciation, that person. Okay. Look at his sequence of work recently, 4-5. Amazing encodings. I mean, you will say how he thought about this. Why didn't I see this myself before? Okay. And simple problems, clever ideas, and so much space is there to play with. Okay. Okay. Right.
Let's, in the interest of time, let's
sit behind this thing. You'll have to exit from that door.
Hello, hello, hello.
Probably use this one.
Test. Okay. Yeah. All right. Great.
Because there was no requirement of
Okay, let's get going. So this is the first of the two invited talks that we have in this winter school. And it's my great pleasure to introduce Clark Barrett, a good friend and actually my former office mate. We did our PhDs together. So Clark is currently a professor of computer science at Stanford University. And prior to that, he was at the Courant Institute of Mathematical Sciences at New York University. And Clark actually developed the technique as part of his PhD that we know today as SMT solving. So we're going to be hearing from the creator of this technology. I remember lots of group meetings where Clark would tell us about CVC. CVC, the very first version, was being developed at that time as part of Clark's PhD work. So Clark is currently interested in automated reasoning and its applications, and he has done seminal work in this area and applied it for hardware verification, software verification, and also verification of machine learning systems, machine learning models. He's currently the director of the Stanford Center for Automated Reasoning, Centaur, yeah, and also the co-director of the Center for AI Safety, right? So without further ado, I'd like to welcome Clark to teach us about SMT solving.
All right, thank you so much. Can you hear me? Great. Thank you so much. It's a really pleasure to be here. And yeah, I wish I had time to tell you about all of the interesting things we're doing, but feel free to talk to me after if you have more questions. All right, so to start with, we're going to have a fun little guessing game. There's a research area in which recently algorithms have improved by orders of magnitude. Computers can solve tasks better than humans. They can solve tasks without help from humans. There's big investments being made by the government and industry, including big tech companies, and it can be described by two letters. The first one is A. Anyone know what this research area is? AR, of course. Automated reasoning. Yes. Can't imagine you would have thought of anything else. All right. Yeah, so this is a very exciting area, despite what you might think about the areas being hyped. And I want to tell you a little bit about why. All right, so we'll start with a very brief history of automated reasoning. So from time immemorial, philosophers have dreamed of machines that can reason. And the pursuit of this dream has led to great accomplishments and great disappointments. We can go all the way back to Leibniz, one of the inventors of calculus. But you may not know this. He also had this dream that one day philosophers would no longer need to dispute. They would just sit down at a computing machine and say, let us calculate. And the calculation would tell them the answer to their dispute. Hilbert in 1928 posed what he claimed was the most fundamental problem of mathematical logic, the Entscheidungsproblem, which was, does there exist an algorithm for telling us whether a particular statement in first-order logic is a valid theorem or not? Okay, and he believed that there was such an algorithm and that this would be a really important step forward. Now, of course, Church and Turing gave everyone a lot of trouble when they came along and showed that there was no such algorithm. In fact, that's an undecidable problem, and people were very sad and disappointed. But there was some hope because a few people said, well, maybe you can't decide that problem, but if you limit it a little bit and say, we're just looking at arithmetic, then maybe we can decide the problem, okay? So there's this whole sort of interesting history going on with logicians and philosophers and mathematicians. But I would say that at the turn of the century, there was still this sort of feeling that this idea of automated reasoning was kind of a failure. It was sort of an interesting theoretical thing that people could go work on, but you're not going to solve real problems. Why? Well, because there are fundamental decidability and complexity barriers, so just forget it. This is like 23 years ago, yeah. I I would say in the late 90s, this was still the general feeling. Okay, so then something interesting happened around 2000. There was a research group at Princeton led by Sharad Malik. And in fact, there were a couple of undergrad students whose job was to get ready to build a SAT solver in hardware. SAT is the Boolean satisfiability problem. So they took the current best SAT solver, which was called GRASP, and they said, well, this thing is written in C++ and it's object-oriented. That's not going to work. That's not going to be a good model for our hardware. So let's rewrite it. Let's put, everything in one big chunk of memory. We can't afford to do these expensive heuristics. Let's just do these really fast heuristics instead. And whoa, all of a sudden, their little software prototype was pretty good. In fact, it could solve a bunch of problems. And this is sort of the beginning of what some people call the satisfiability revolution, where all of a sudden we could use SAT solvers to solve some hard problems. And how could this be? Did somebody suddenly figure out a way to solve NP-complete problems in polynomial time? No. But it turns out that in practice, many of the interesting problems we run into that we care about, that we'd like to solve, they don't exhibit this worst case behavior. And so there was sort of a resurgence of interest in automated reasoning. About that same time, Supertik and I were sharing an office in Palo Alto. And one of the things I was working on is, can we take these new fast SAT solvers and combine them with some more powerful reasoning to give us even more powerful automated solvers? And that was when this idea of satisfiability modulo theories was born. So what do we have now? What are these SMT solvers? Well, the big idea is that this is a general purpose logic engine, okay? You want to solve some problem in logic, give it to the SMT solver, it will solve it for you. And why is that useful? Well, there are a lot of problems that have this kind of feeling where, given some condition X, is it possible for Y to happen? Now, if you can represent X and Y using logic, you're golden. You can give it to the SMT solver. And the nice thing about SMT is you have a quite rich logical language to describe X and Y. You're not limited to Boolean, just Booleans, which is what's true in SAT. And so I would say that SMT solvers, SAT solvers too, to some extent, but also SMT solvers, are really changing the way that people solve problems. So it used to be that if you wanted to solve a particular problem with search, like this chess problem, right? Then you would go build your special purpose, search algorithm and run it. But now instead, you just have to figure out how to translate your problem into SMT, run an SMT solver. Not only is that an easier process, a lot of times it's faster because the SMT solvers have been highly tuned. And just to prove the point, here I've translated the chess problem into the language of Pono, which is our SMT-based model checker. So how did I do it? Well, I said there are 10 spaces, okay? And for each of them, we're going to give it essentially a bit vector of size 2. That's what this A1 to A10 is. Why 2? Well, because each position has 3 options. Either it's empty, it's white, or it's black. So I would like to do it with 3, but 3 is not a power of 2. So I'm going to do it with 4 different possibilities, and I'm just going to ignore the 4th one, right? So 0 means empty, 1 means white, 2 means black, and 3 means nothing. And here's my initial state constraints here. So I say, to start with, positions 1 and 3 are 2, 6 and 10 are 1, and the rest are zeros. And then we're going to have, now I wasn't going to talk about model checking, but this problem came up, so I'm going to say a little bit about model checking. So we have an initial state. So the initial state just says what are the values of all of these variables at the beginning. And then we have what's called a transition relation. What's that? Bigger? Yeah. That better? Okay. All right, so we have our variables, we have our initial state, and then we have what's called the transition relation. And the transition relation tells you, in the current state, how do you get to the next state, okay? So what I did is I have another variable called move. Move can take any value from 0 to 8. If you look at this, how many edges are there here? There's 9 edges. And so each edge can go both ways, right? So there's actually 18 possible moves. Now I was a little clever because what I'm going to do is I'm going to actually represent each of these as a single move and just say that two things can swap places as long as one of them is empty. In fact, I don't even care what the other one is. I'm going to allow a move that just swaps two empty squares because that's not going to make any progress. So I probably won't use that move if I'm trying to get to a certain solution. All right, so I've got 9 moves. Let's just look at the first one here. It says, if the move is 0, the value of the move is here at the end, then as long as either position 1 or 6 is equal to 0, then A1 becomes A6 and A6 becomes A1. Otherwise, everything stays the same. And also everything that's not A1 and A6 stays the same, okay? And if you look at the rest of these rules, there's just, there's 9 of them. They all basically do one of these edges, okay? And then finally, we say we're trying to prove something. We're trying to prove that it's impossible to get to the state where A1 and A3 have values 1 and A6 and A10 have values 2. So we're trying to show that you can't reach the state where the two things are swapped. Okay, and then I just have this invariant that says the moves have to be less or equal to 8 because, again, the move is a vector of size 4, and so it could have values that are too big. All right. Now I have a little program here called Pono. Pono is our SMT-based model checker. What it's going to do is it's going to take each transition, represent it as an SMT formula, and then call our SMT solver. I think it's calling CVC5, might be calling Boolector. Anyway, we've got it hooked up to lots of SMT solvers under the hood. And it's going to say, can I break that property in 1 step? If it can't do it in 1 step, it's going to try to do it in 2 steps. If it can't do it in 2 steps, it's going to try to do it in 3 steps, and so on. So great question. In this particular version, it's not learning anything. It's not doing incremental solving, but that would be a nice optimization. Yeah. In fact, separate talk, we have another piece of work where we actually learn how to solve using machine learning. You do some training on small unrolls to help you solve the larger unrolls faster. We had a paper in FMCAD that was pretty nice. Okay, but here we're just doing the basic thing. We're just unrolling it and calling the SMT solver. Okay, so I'm going to let it run up to 40 times. Okay, so it's checking. Can't do it in 32 steps. Can't do it in 33. You know, it's thinking hard. It gets a little harder as the steps get bigger. The search space gets bigger, right? Now it's thinking really hard. 37, 38. Wow, how many steps does it take to unroll this thing? 40 is the answer. All right, so now we have the answer to your question. It takes 40 steps. All right, and you can look at this and just look at which move was taken in each step to see exactly how to do it. All right, so anyway, that was a digression. But that shows you that if you want to solve a problem, so yeah, that was a lot faster than writing your own piece of code to solve that problem, right? You know, I have another good story I can't resist. When I was an undergrad, I took this combinatorics class, and one of the problems we had to do was show that a particular Ramsey's number was larger than 16, which amounted to showing that on a perfect graph, of size 16, so all the edges connected to all others, if you color it with 3 different colors, there's a way to color it so that there are no triangles all of the same color. Okay, we had to show that this was the case. So of course I tried it a little bit. I was like, this is too hard. I wrote a program. The program ran all night. Next morning, it's still trying to find a way to color those edges. I came in all frustrated. One student in the class had solved it because they figured out it was equivalent to some crazy thing with abelian groups. And I was like, that's not fair. This is not a class about group theory. I even made my dad write the author of the book and say that wasn't fair. But years later, I learned about Sat. and I plugged it into a SAT solver, and like within a second, it had the coloring, okay? So these things are quite powerful. All right, good. So they've also been getting better and better. So this is kind of exciting. Back in 2010, if you take a set of benchmarks, these are bit vector benchmarks, and you ran sort of the best solver at the time on this set, it would take something like, 4,500 seconds to run. And then as the years go by, you can solve them faster and faster. This was just a little case study we did a few years ago. So the average speed up is an order of magnitude. That's pretty cool. But what's even more exciting is there were about 3,000 problems that were completely unsolved in 2010. All but 200 are solved in less than a second. Okay, so this goes back to what you heard in the first talk. It's not because we, made any fundamental breakthroughs in complexity theory. It's because we have smarter heuristics and ways to approach these problems that work well in practice. All right, and here's, yes.
The problems that humans can solve or machines can solve? Can't solve.
The machine, well, the humans can't solve them. No way. They're like hundreds of megabytes of. Hold on. They look like this, right? So good luck. Get out your pen and paper and see if that's a valid formula, right? But no, the best algorithms, the best automated reasoning algorithms couldn't solve them back in 2010, and now they're solved. Now the best algorithms solve them in less than a second. Yep. Okay, and here's a really fun application. So I found out about this when I was attending the Federated Logic Conference in 2018. I was in an industry talk, and Byron Cook from Amazon got up and said, hey, we have this great new thing we're doing at Amazon. It's called Zelkova. And basically what we'll do is we'll take a security policy that our users write that tells you who can access data in the cloud. We translate it into an SMT encoding, and then we call SMT solvers to check whether the security policy that they wrote is better than certain guardrail policies, right? And guess which is the most important guardrail policy? It's called public, right? Your policy that you wrote had better not be equivalent to, I just made it open to the whole internet, which it turns out people do a lot when they make mistakes. You mix up an and an or a negation, and then suddenly when you're trying to deny everyone access, you gave everyone access. So they run this every time somebody commits an access policy, and they call SMT solvers billions of times a day. All right. So that's a pretty important use case. All right. So you know how in a movie there's like the exciting first part that gets your attention and then it rolls the credits? Okay, now we're to the credits. So this is my talk. It's going to be about SMT. And I need to acknowledge some people who contributed material. And of course, we'll only be able to scratch the surface on everything that's SMT solving. But I'll do my best to give you a good taste. All right. So now let's just look under the hood a little bit. What is an SMT solver? So an SMT solver has this sort of an architecture. Basically, you've got a SAT solver, and we're not going to talk about what a SAT solver is and how it works very much, but basically it's going to solve the propositional satisfiability problem. So you give it a formula with just Boolean variables and Boolean operators, and it'll tell you whether there's a solution. All right, so we're going to leverage, all the great work that the SAT community does, and we're just going to plug in the very latest and greatest SAT solver. Now, we also have this thing called a core. Well, what actually happens, let me tell you a little bit more of what happens. The SAT solver doesn't see the whole problem because the whole problem has this theory stuff in it. So the SAT solver only sees the Boolean skeleton of the problem. And then what happens is it works on that Boolean skeleton, and every time it decides to set a variable to true or false, it just sends off a little notification to the rest of the system. Okay, so what happens? Well, there's this core. The core is receiving these variable values coming from the SAT solver, but it actually knows what those are equivalent to in the theory world. And it says, you set variable 5 to be true. That happens to be equivalent to x less than y. So I'm going to go notify the arithmetic solver that now we know that x is less than y, right? So it does this kind of arbitration, sends these assertions to the right things, and it handles this technical thing called theory combination that I'll talk about later. Okay, then you have the theory solvers. Now, what's nice about this architecture is the theory solvers don't need to deal with any kind of propositional structure. They just get a set of facts, x less than y less than z less than x. And their job is just to say, is this set of facts consistent in my particular theory? And they're designed to know exactly how to solve problems in their theory and nothing else. Now, they should also have some other properties in order to be efficient. Incremental, meaning if I ask you whether these two literals are consistent, and now I add a third one to the mix, you shouldn't have to start from scratch. You want to sort of, this go back to Supertick's question, you'd like to be able to build on what you've already done. Backtrackable means maybe I gave you 10 facts, but now I want to jump back to only 5 facts. You should be able to do that quickly. You need to be able to do something called conflict generation, which is if I give you 10 facts and you say, nope, those are inconsistent, you better give me back a subset of those 10 facts that are actually inconsistent, the smallest subset you can. And then they can do something called theory propagation, which is if the theory figures out that some variable has to be true or false, it can actually tell the SAT solver that. Okay, so this is like the big picture of how things work. And I'll explain this in more detail later. All right. Oh, that's interesting. Is that me or you? That's you. All right. Okay, so let's put a pin in how the theory solvers are going to talk to the SAT solver, and let's just zoom in a bit on these theory solvers. All right, so the idea is that given some logical theory, and here you can think of this as a set of sentences in logic that are closed under deductive consequence. You could also think of it as a particular theory like arithmetic, where everything means exactly what you expect it to mean in arithmetic. Plus means plus, minus means minus, 0 means 0, and so on. But basically, a theory is a set of operations and a meaning for those operations. So given such a theory, now we're going to take a set of literals, where a literal is just a theory atom, which is just a fact in the theory that's either true or false, or the negation of a theory atom. And it's going to determine whether that a set of those is consistent, meaning there's a solution that satisfies all of those literals. Right, and a set is T satisfiable if there is some solution or some model that satisfies every formula. Okay, and then let's look at some specific theories of interest. Okay, sort of the simplest theory is something we call equality with uninterpreted functions. And this just means that the theory doesn't impose any additional restrictions on the symbols that aren't already imposed by the logical structure itself. So logic requires that a function is a function. And that's it. So basically, if I write ABC, ABC can have any value at all. If I write f of x, f can be any function at all. Okay, that's this logic. And what is it useful for? Well, it's actually quite useful if you have some complicated piece of structure that you're trying to model, and you actually don't care what that structure is doing. You just want to say, well, this structure is doing something, and any place I see that structure is doing the same thing. I can just abstract that whole thing away and replace it with an uninterpreted function. So here's an example, right? So if I want to solve this problem in arithmetic, where I've got multipliers and absolute values and addition, if you look at this carefully, it turns out that you can show this is unsatisfiable, but you don't actually need any arithmetic reasoning to do it. And to see that, you subtract this by writing these uninterpreted functions here. And then you can see Well, can I see? Let's see. How hard is it to see this? If you set A equals to B, I guess that's a unifier for these two expressions, right? And so then you basically have big expression equals D and big expression not equal to D. And so that's going to be unsatisfiable. Right, so that's a useful trick. You know, one of those tricks that makes things faster is you see something hard and replace it with something simple in a conservative way. And if you're lucky, then you can solve the problem. All right, another theory that's really useful is arithmetic. And in SMT land, we divide arithmetic up into a whole bunch of different layers. And the reason for this is that each layer adds some complexity, and we'd like to solve it with the simplest possible layer, right? So if all I have is bounds, right, I have a bunch of variables, x equals 5, y less than 3, right? If that's all I've got, then there are extremely fast algorithms to solve that, okay? If I have something called difference logic, where every constraint is of the form x minus y, some comparator with a constant, right? X minus y less than 5, x minus y equals 7, something like that. Then this is called difference logic, and we have ways to solve that. Then you can have UTVPI, which is unit to variable per something, which is a little more general than difference logic. Next up, linear arithmetic, right? You can have any linear sum, as long as you don't multiply two variables, and then ultimately nonlinear arithmetic, where you have polynomials. Now, everything up to linear arithmetic is pretty easy to decide, at least for the reals. For integers, linear arithmetic gets a little harder, but it's still decidable. For nonlinear arithmetic, it's decidable for the reals, but not for the integers. And even though it's decidable for the reals, the complexity gets pretty bad. So basically, you'd like to sort of stay in this linear or better, but there are some interesting algorithms for nonlinear that can solve a lot of problems these days. All right, here's another theory of interest. This is the theory of arrays. So this is useful if you want to model, well, arrays in programming, or maybe memories in hardware. And basically what it is just you've got a variable that represents some big array of things. And you just need these two axioms to describe what it is. So there's two operators called read and write. Read basically says, given an array and an index, just give me back the value at that index. And write takes an array, an index, and a value and says, I'm going to update this array with a new value at this index, and returns the new array. So we can axiomatize it by saying, if I read at the same position I wrote, I better get the same thing back. And if I read at a different position, then I better get whatever was in the original array at that position. Now, if you want to reason about equalities between arrays themselves, you also need this extensionality axiom that says that if all the positions of an array are equal, then the array themselves are equal. All right, and here's a little quiz. Is the following set of literals satisfiable in the theory of arrays? What's fun is I haven't looked at this slide long enough that I have to figure it out myself too. So we'll have a race. Let's see. Yep. Any thoughts? Implication should be the other way around, or which one? No, so the other way around, we don't need an axiom for it because it follows from the properties of functions. But to know this, you need an axiom. The axiom says that if all the values are the same, then the array should be the same. That doesn't follow from just logic. It is not satisfiable. That's correct. Yes. So if you stare at it long enough, you'll see that, well, if I equals j, then that read over write constraint means that x has to equal y, right? But if x equals y, then that means that reading, and A equals B, right? So that means if we read from B at I, it's the same thing as if we read from A at I. But this says that if I write X into A at I, then I change the value of the array. But we know that B has the same value at I that A does, so I didn't change the value of the array, right? So that can't be true. All right, so you can, twist your brain around a bit trying to figure these things out, or you can write a nice little program to figure it out, which is what I like to do. Yes? Not for this problem, it's not. But in general, so if I have a disequality between arrays, like A not equal to B, then what I'd like to be able to conclude from that is that there exists a position in A that's different from the position in B, and I can't do that if I don't have that axiom. Yeah. Okay, another important theory is the theory of bit vectors. So this is basically a theory where every object is a string of bits of some size. Could be, it's an arbitrary but fixed number of bits, like 10, 20, 32, 64. And then we have all sorts of things you can do with these bit strings. You can do machine arithmetic, which is arithmetic mod 2 to the n, right? Which is exactly what computers do. You can do these sort of bitwise operators like and or. You can do string-like operators where you concat them and extract slices. And these are exactly the sorts of things you can do in programming languages and with hardware description languages. So this is a very useful theory for reasoning about computer systems. All right, so now we have another little quiz. Is this formula satisfiable? So let me tell you what some of this means. If I write bracket 1 to 0, it means select out the slice that goes from 1 down to 0 of this bit vector of size 3, where this is, so it's the two least significant bits of A. The vertical bar is a bitwise OR, and the plus here would be plus mod 2 to the third, so plus mod 8. Oh, no, it's not, because you selected 1 bit out, so it's plus mod 2. Yeah. Okay, why is it unsatisfiable? All right, cool. Very good. Yeah, so you can usually figure out these little ones yourself, right? Shows whether you're following along. Very good. Okay, so now I'm going to tell you, so that's like a quick sampling of interesting theories. There's lots more. There's theories of strings and sequences, theories of data types. A new one that we just implemented is a theory of finite fields. And sort of every year or two, we'll add more theories to the mix and find interesting ways to use them. Okay, but now the next question you might have is, well, that's great. How do I implement a theory solver? How would I actually build an algorithm to detect this? So we'll look at a very simple example. Difference logic. So remember, in difference logic, each atom has the form x minus y, some comparator, and a constant. Okay? And the comparators can be equal or any kind of strict or weak inequality. Now, of course, the variables can range over integers or reals, and those are two different flavors. That we have integer difference logic or real difference logic. Okay? And the QF here, this is SMT-lib nomenclature. It just means quantifier free. So I think I'm not going to talk about quantifiers at all today, which is too bad. But basically, the core engines of SMT solvers are all quantifier free. And then if you want to reason about quantifiers, then there's this whole other stuff you have to do. Okay, so difference logic. So step one, this is actually pretty typical. The first, often what you do is you say, okay, the full language I'm trying to decide is too big, so I'm going to figure out a way to reduce it to some core language. And I'm going to do that with some rewrite rules. So if I have an equality, I'm just going to rewrite that into two inequalities in a conjunction, right? X minus y equals c. That's the same thing as x minus y less than or equal to c, and x minus y is greater than or equal to c. Okay? If I have a greater than or equal, well, for difference logic, what's kind of cool is I can convert that into another difference logic formula that is a less than or equal. Okay, I just negate both sides. So that's great. If I have a strict greater than, I'm going to flip it to a strict less than. And then the strict less than is a little bit tricky, but for integers, there's a clever thing I can do. If x minus y is less than c, well, because the next value below c is the next integer down, I know that x minus y has to be less than or equal to c minus 1. So I can easily do that. Now for reals, it's not so easy. And the current best technique is to introduce a new little variable called delta. And then you have to do all of your calculations using what's called delta arithmetic, where you carry around this value of delta. And then at the end, you can figure out what's the value of delta that ensures that everything works out. So we're not going to talk about that. There's some nice papers about it. We're going to look at the integer case. Okay, so once we do this rewriting, we have a conjunction of literals. They all have the form x minus y less than or equal to constant. So now here's where you have to think a little bit. And of course, for every theory, it's going to be a little different. For this theory, it turns out there's a nice graph algorithm for solving this. So if you form a weighted directed graph where there's a vertex for each variable, okay, then we're going to draw an edge from variable x to y of weight c if there's a constraint x minus y less than or equal to c, okay? And then it turns out, you can prove this, that the set of literals is satisfiable if and only if there's no cycle that has a negative weight, okay? And there's some algorithms for detecting that. All right, so let's look at an example. So let's say I give you these 5 constraints and ask you whether this is satisfiable. So armed with your new knowledge, we're going to do exactly what I suggested. So first, we convert everything into less than or equal. Okay, so just apply those steps. We started with 5 constraints. Now we have 7. So we got a couple more constraints. Now we draw the graph. Looks like this. So are these constraints satisfiable? Where? Very good. Yes. So there is a negative cycle. That -3, -1, 2 adds up to -2. And so sure enough, this problem is unsatisfiable. All right. Now, we're going to take a little pause. And I'm going to give you a preview of what you're going to do this afternoon. It does, yes. Yeah, so if there are no negative cycles, what you can do is add a new node to the graph, call it 0, and then find the shortest path. Let's see, connect it to all of the other things with a weight 0, and then the shortest path from that to every other thing gives you the value. Yeah. Okay. Oh, how fast can you find negative cycles? So, well, the Floyd-Warshall algorithm is a cubic algorithm. There are faster algorithms, I think, in practice, but I'm not going to tell you because that's your job in the lab. So in the lab, what you're going to do is you're going to get a copy of our SMT solver, CVC5. It's going to come with some skeleton code for an integer difference logic solver, but it's not going to have the rewrites, and it's not going to have the negative cycle detection, okay? So you're going to have to write that part yourself. By the way, if you're thinking ahead, you might want to already go to this project page and at least try to get CVC5 built. Probably it'll work for you. It works pretty well on Linux and Mac OS most of the time, but just in case, you might want to get started earlier. To find this page, let me tell you what you do. So first you type CVC5 into Google. Okay, that'll take you to the CVC5 page. Then click on the GitHub cat. That'll take you to the GitHub page. Then up here in the upper left, these are the branches. You're going to scroll down, view all branches. Whoops. You're going to pick this IDL lab, integer difference logic lab. And finally, scroll down and click on project. Okay. All right. So I'll give you a second to think about that. Anyway, if you find my talk boring, you can switch over to installing CVC5 and get ahead of things for this afternoon. Okay, did everyone see how to do that? Just so that you can get started with the installation. All right, good. Okay, so far we've seen a big picture of what an SMT solver is. It's got a SAT solver talking to a core, talking to a bunch of theory solvers. We went a little bit into what the theory solvers could be and how to build a simple one. Now we're going to come back to the question of how do you combine these theory solvers with the SAT solver? Like, what does that thing look like? Now, it's going to be useful in this case. We're just going to collapse all the theory solvers into one for now. Just assume we have one theory solver and one SAT solver, and they have to talk to each other. All right. So recall, a formula is satisfiable if there's a model that satisfies it, makes it true. It's unsatisfiable if there's no such model. And the t-satisfiability of quantifier-free formulas is decidable if and only if the t-satisfiability of this conjunctions of literals is satisfiable. Why is that? Well, because you can basically enumerate all of the SAT models of the Boolean skeleton and then check each one, right? So it may not be very efficient to do it that way, but it is decidable. But in practice, that's not what you want to do. You don't want to enumerate all the possible models. What you'd like to do is have the SAT solver work on the Boolean part and the theory solver work on the theory part and have them work together. So how do they work together? Well, you know, it's not as easy as you might think. Yeah, go ahead. Let's see. Yeah. Good. Okay, so just to set your expectations here, there is a little bit of interesting stuff here because answering this question is basically what I did for my PhD, right? So if you just try to plug the SAT solver to the theory solver and press go, it doesn't work very well. You need a little bit more than that. All right, so what do you need? That's what we'll find out here. Okay. So first of all, let's just think about how might we use a SAT solver to help solve these theory problems. So there's an approach that I won't talk too much, but it is actually quite useful and sometimes it's the best approach. And that is, who needs all this SMT stuff anyway? Just give me the problem. I'm going to figure out how to encode the whole thing into SAT, and then I'm going to take, you know, Armin or Marine's latest and greatest thing, and it's just going to blow it out of the water, right? Well, sadly for us SMT people, this actually works really well a lot of times. So in fact, for the theory of bit vectors, this almost always is the best thing to do. However, if you have a problem that's got some complicated arithmetic with some data types and some arrays, and then you start scratching your head, how am I going to convert that whole thing into SAT? Sometimes that doesn't work so well. There was this really nice system from Sanjit Seshia called and Randy Bryant, I guess I should say his advisor, right, called Euclid, that was quite powerful and could solve a lot of problems really fast with this eager encoding. I think there still is a system called Euclid. Now there's Euclid 5 and it does more than this, but yeah.
So the eager encoding will only work for decidable like bit vectors and stuff. I mean, it will never work for integers.
Well, okay, so integers, well, without multiplication are still decidable. Okay. And there are eager encodings. In fact, there's a whole line of work from Ofer Strickman back in the day, but it didn't work very well. That was the bottom line. So it works sometimes, and when it works, it's great. But then it just gets pretty hairy. Yeah. So basically, if you can figure out a way to make this work, that might be the way to go, or at least try it. If you really want to do this very rich sort of modeling with lots of different theories, we have another thing for you, and that's called the lazy approach. Now, the reason it's called the lazy approach, I'm not totally sure I know why, but I'll take a guess. The very first paper I wrote about this was called Solving Problems by Incremental Translation to SAT. That's one way to think of what you're doing in SMT, because what you do is you take this Boolean skeleton of the problem, and then the theory solvers, every once in a while, tell the SAT solver more information. They say, no, that's no good. You can't do that. You can't go down that branch. And eventually the SAT solver says, well, you just tied my hands. I can't do anything anymore, and says unsat. And what you've done is you've essentially done you've done exactly what you would have done for the eager translation, but only for the parts that really matter. So that's why we call it lazy. It's like basically taking just enough information from the theories to make the problem unsatisfiable in the SAT world. Okay, so the big idea, you abstract the problem, give it to a propositional solver, a SAT solver, and then every time the SAT solver thinks it has a solution, you check it with the theory solver, say, is that okay? If it's not, then you refine and keep going. And most SMT solvers follow this approach. And that's what we'll focus on. Okay. All right, so to start with, this is the first thing I tried, right, in my PhD work. Let's try the very lazy approach. So what we're going to do is we're going to take a problem like this one. Okay, so here we have g of a equals c. That's going to be one SAT variable. F of g of a is not equal to f of c. That's another one. That's the negation of a variable. Or g of a equals d. So this is a disjunction here. And c not equal to d. Okay, so we're just going to take an offline SAT solver. We're going to take some non-incremental theory solver. We abstract these theory atoms into propositional atoms like this, right? So we have variable 1, variable 2, variable 3, variable 4. And then we can just send this simple problem to the SAT solver, right? We've got 1, we've got not 2 or 3, and we've got not 4. And say, hey, can you find a solution for this problem? SAT solver says, sure. Set 1 to true, 2 to false, and 4 to false. Solves it. Theory solver goes, looks at what that means. It means g of a equals c, and f of g of a not equal to f of c, and c not equal to d. Well, if you look at that carefully, let's see. Already here, g of a equals c is already a conflict with this, right? Because if the two arguments to f are the same, then the values of f have to be the same since that's a function. So the theory solver will come back and say, nope, that's no good in the theory world. And it says, tell you what, I'm going to add a new clause. The new clause is just going to rule out exactly that solution that you gave me. It says, so if I take 1 and not 2 and not 4 and negate it with De Morgan's laws, I get not 1 or 2 or 4. So I'm telling the SAT solver, you better do something different from what you did last time. Either 1 has to be false, or 2 has to be true, or 4 has to be true. You can't have everything the same as it was last time. That was no good. Okay, so now the SAT solver tries again, comes back with a new model. This time it says, all right, that's fine. I can still set 1 to true, 3 to true, and 4 to false. Okay. Now, if you look at this one, let's send that to the theory solver. We put on our theory solver hat for a second. Well, if g of a equals c and g of a also equals d, then by transitivity, c has to equal d, right? But 4 says c not equal to d. So that's no good either. So then the theory solver is just going to say, hey, whatever you just gave me, negate that and add that to your list of things. So it's going to add not 1 or not 3 or 4. And now this is actually unsatisfiable just using Boolean reasoning. Okay, so we just gave it enough information about the theory part to figure that out. Okay, so we're done. The original formula is unsatisfiable. Okay. Now, this works, but for any non-trivial problem, it gets slow pretty fast. Okay, so what can we do to make it smarter? Well, the first thing, yeah, go ahead. Yes, it will, because there's only a finite number of possible SAT solutions. As long as your theory solver is decidable, it'll terminate. Yeah. Okay, so notice the first thing that maybe was not such a great idea is we only check the T satisfiability once we have a full SAT model. Now, why might that not be a good idea? Well, let's say that the SAT problem is actually kind of hard, and it has to do a lot of search before it comes up with that first model. And what if the first 2 decisions it made already are contradictory in the theory, right? Then that means you just wasted a whole bunch of time when you could have backtracked right away. So what we're going to do is we're going to have this very fast incremental theory solver where we can just sort of feed it stuff as we go. And that way it'll head off any bad search paths right away. Okay. The other thing that we did is if we get a model M, which is just a set of values to the propositional variables, the theory solver just is basically saying yes or no, right? And if it says no, then we take that model, we negate it, and send it back. So this is also not so smart, okay? And the reason is, again, what if your model has 100 variables in it, but actually 2 of them are enough? Maybe you have x equals y and x greater than y are 2 different things in your model. Those already contradict each other, right? So you can actually give it a much better explanation for why that model didn't work than just saying not M. So what we'll do is we'll identify a subset of the model, and we'll send that back. Now, do you have to take the minimum or minimal subset? No. And in fact, computing the minimal subset that's unsatisfiable is often just as hard as computing unsatisfiability itself. So you don't want to do that necessarily. So what we do, again, what do we resort to? Heuristics, right? So the heuristic is whatever you can do that's fast and easy to minimize that set, do it. And that's a good idea. Now, in some cases, you can get a minimal set for cheap, but not always. Okay, and then right now, we're just saying that as soon as you get, you basically run the SAT solver, stop, run the theory solver, stop, restart the SAT solver. So you don't have to do that, right? Because if your SAT solver also has the ability to be incremental, you can basically just add a clause and keep going. Why is that a good idea? Well, because the SAT solver learns a bunch of stuff as it goes, and that way it'll get to reuse everything it's already learned. So we'll just backtrack. We'll just add a clause and backtrack, but keep running the SAT solver as well. Okay, so those are the big ideas. And now I'm going to show you how these work in more technical detail. So what are the benefits of this approach? Basically, each tool does what it's good at. The SAT solver is good at Boolean. Theory solver is good at theories. The theory solver doesn't have to think about Boolean connectives, which is a big pain, right? You just have to look at conjunctions, so that's great. It's also very nice and modular, right? Somebody comes up with a new SAT algorithm, you can just plug it in. Someone comes up with a new theory solver, you can plug that in. So this is great. By the way, there's some really nice new work that's relevant here, which is I don't know if you've seen this IPA-Sur. So right. So this is basically, there's a lot of SAT solvers out there. And so a group of people got together and said, hey, we should have like a standard interface for calling SAT solvers. So that's what the IPA-SIR thing is. And then some more people came along and said, well, actually, a lot of times SAT solvers get used embedded in another system, and you need a little bit more than just this IPA-SIR. So they have this IPA-SIR up, UP for user propagators. And actually, this is great. So when this came out, we basically took our SMT solver, ripped out the old, totally hacked SAT solver from like 20 years ago, plugged in the very latest and greatest SAT solver that implements the IPA-SIR up interface. And well, after a few months of hard work by my extremely talented research scientists, it works. So now CVC5 uses this interface. And the cool thing is, anybody who writes a SAT solver implements that interface, we can plug it into CVC5. So that's great. Okay. All right. So yeah, I think we have time for this. So the last thing I want to talk about this morning is something called, basically we're going to look at an abstract formal framework. We're talking about all the things that I've been sort of waving my hands about in terms of the way that the SAT solver talks to the theory solver. So the way we're going to do this is we're going to model it as a transition system, okay? And you'll see what this means. And we'll start by just building a transition system for the SAT problem, and then we'll show how we can layer on top of that transition system for the SMT problem. So why is it useful to even show you an abstract framework? Well, an abstract framework sort of lets you get to the heart of what are the important algorithmic ideas without showing you pseudocode or having to read pages and pages of C code. So basically, you're going to get the key ideas, and once you understand the key ideas, you could go write your own SAT solver without too much trouble. Okay, we can though actually model some of the key implementation features by making our transition system slightly more sophisticated, and we'll do that. We can compare strategies, and we can actually give some guarantees. Okay. So the abstract framework is based on the original DPLL procedure. This is Davis, Putnam, Logeman, Loveland. Curiously, the four of them never wrote a paper together. There's a paper that Davis and Putnam wrote, and then maybe Davis, Logeman, Loveland wrote the other one. And actually, it's the second one that we call the DPLL, but they were written sort of the same time, and everybody was working on it, so we give them all credit. So how does the DPLL algorithm work? Well, basically, you try to incrementally build a satisfying truth assignment for a propositional formula. You either guess or you do some inference if you can. And there's 3 rules, but you can kind of ignore one of them I won't talk about. Basically, all modern SAT solvers are based on 2 of those original rules, which is unit propagation and guessing. Okay. All right. And if you get the wrong guess, then you backtrack. So in order to explain this abstract framework, we need some notation. So I said I'm going to explain it as a transition system. So what's a transition system? Well, it's just like a finite state machine. So you have some states, and states can go to other states. And we're going to use this idea of a state machine or a transition system to talk about how the algorithm actually functions. So we're going to have 2 kinds of states. One is the fail state. If you ever get to the fail state, you know your problem is unsatisfiable. All right. All of the other states are a pair of M and F, where M is a partial assignment, and F is actually the formula you're trying to solve. Okay. Now M actually has a little bit more information in it. So it's a sequence of literals. If a literal appears in M, it means you've assigned that literal true. Remember, a literal is just a variable or the negation of a variable. And M can also have in it these decision points, which are these big dots. And if you see a dot in the sequence, it means the next literal is there because of a decision, not because of some other reason. Okay? All right. And then here's another technical little definition here. This assignment M is going to look like a bunch of literals, dot, bunch of literals, dot, and so on. And so each dot denotes another, what we're going to call decision level, okay? So the first sequence before there are any dots is decision level 0. The next sequence is decision level 1, and so on. And we're going to use this notation. M sub I refers to just the literals in one of those sequences between two dots. And M bracket I means everything up to the ith decision. Okay. What's the initial state? So the initial state of our transition system is just the formula you're trying to solve in the F slot and an empty sequence in the M slot. Okay, so we don't know anything about any literals or decisions yet. It's just empty. And what do we expect to reach as a final state? If it's unsatisfiable, we expect to reach this fail state. Otherwise, we're going to reach a state where we have some formula, call it G, and some sequence called M, where actually, if you just plug in all the true for every literal in M, it satisfies G, makes G true. Okay, that would be the other final state. All right, so how do we do it? So we're going to explain the transitions now as these guarded assignments, where we put on top some conditions on the states for which this particular rule applies, and then on the bottom, it tells you how that rule modifies the state, okay? You'll see an example in a second. All right, here. So here's an example. It says, if I have a particular clause in F, okay, so remember F is my formula. I think I forgot to say, we're assuming everything is in conjunctive normal form here. So conjunctive normal form just means that you have a conjunction of clauses where each clause is a disjunction of literals, where a literal is either a variable or the negation of a variable, okay? So everything in F, right, and then we're also going to treat F, which is your formula, as a set of clauses where there's an implicit conjunction, okay? So it's a conjunction, but we're just going to take the set of all the clauses. That means the conjunction of all those clauses. All right, so the propagate rule says if there's a particular clause in F, which is this L1 or up to Ln or L, okay? And if each of L1 through Ln has a negation in the assignment, and L itself doesn't appear either by itself or negated in M, then we can go ahead and add L to the assignment. All right, this is the essence of what's called unit propagation in sat solving. So why does it work? Well, you've got some clause, okay? A clause is a disjunction. How do you make a disjunction true? Well, at least one of those literals has to be true, right? So what this rule says is once you know that all but one of the literals is false, that last literal had better be true, right? Because if it's not, there's no hope to satisfy that clause. So this was a basic observation already made by Davis and Putnam back in 1960. They said, hey, if we turn everything into conjunctive normal form, then there's this really cool thing we can do, which is notice that if all but one become false, we can assign that other one to true. And that speeds up our search, okay? And these days it's called Boolean constraint propagation, and it's still, for many problems, it's where most of the time is spent by the sat solver, is just cranking through as fast as it possibly can this propagate step. Should not be underestimated how important this is. If you didn't do this, problems that we can solve in less than a second would take years. There literally exist problems like that, okay? So this is super important. All right. Now notice that here we're treating M as a set. when I told you it was a sequence. All right, just, slight abuse of notation, just treat it as the set of all things in the sequence whenever you see that. And another little minor note, we're going to treat the clauses modulo, associativity, commutativity, idempotence. So if there's a clause which you can rearrange in any way to look like this, then we'll apply it, right? So in other words, it doesn't matter where that last literal is. It doesn't have to be the last literal in the clause. It could be in the middle, and you still can apply this rule. Okay. Next rule, the decide rule. So this just says that if you have a literal that appears in your formula, actually, the literal or its negation appears in a variable or its negation appears in the formula. Sorry, no. If you have a variable that appears in the formula, then either the variable or its negation is in this lit set, okay? So you can decide the variable to be true or false. You can pick. So if you have a literal, it's not already decided, you can add it to M, but you have to add a dot to say, I don't know this is true, I'm just guessing this is true, okay? And we're going to have to eventually get rid of all the dots because we're not, if we want to show that something's unsatisfiable, we have to explore all possible values. Okay. And then we have this fail rule. So the fail rule says if I have a clause and every single one of its literals is false, well, can't do much, can I, right? I can't make any further progress. I'm stuck. And then I don't have any decision points. So nothing in my trail is a decision. Everything was forced. Then I know that the problem doesn't have a solution because there's no way to backtrack. Okay, so that's the fail rule. And of course, the other possibility is I get stuck, but I can go back and undo a decision. So what I'm going to do is, let's see. This is clever, right? So I have some, right, I have some clause. All of its literals are false, okay? And then basically, I just look at the suffix of my current assignment here. This is also called the trail. I might use the word trail. If I look at the suffix of the trail, I go to the very last decision and I undo that one. And I take the opposite branch, okay? This is called chronological backtracking because I backtrack to the most recent decision. Now, there are cases where I can backtrack even further, which I'll show you in a bit. That what? You don't have decision. That's right. That's right. So the decision means I'm guessing, but once I've guessed one way and that didn't work out, now I'm no longer guessing anymore. It's forced to be the other way, so I can take out that decision dot. That's right. If you didn't do that, then you wouldn't terminate. Yeah. Okay, now that's basically how DPLL works. Okay, you basically do your unit propagation, do your decisions, and your backtracking, and then run until you either get to a satisfying assignment or you get to this fail state. But modern solvers can do things that are a bit more clever. So they've coined this term CDCL to sort of represent that the current generation of SAT solvers is doing something a bit smarter than this original DPLL. And CDL stands for conflict-driven clause learning. Yeah. Yeah, this decide rule. Yeah, so I just have these 4 rules: propagate, decide, fail, and backtrack. And that's already enough to get a complete decision procedure. But we want to do something a little smarter. Okay, so CDCL solvers, conflict-driven clause learning, this is how modern SAT solvers work. And they do a few things that are a bit smarter and that also really help speed up the search. So in order to model these, we have to add another thing to our set of states. So a state now is either fail or it's a triple, where M and F are the same as before, but there's another thing in the triple called C. C is just going to be a single clause, and C is the clause that's giving us some information about a particular conflict, okay? And we'll see how that works. So the initial state, again, M is empty, F is the problem we're trying to solve, and C has a special value called no, which means there's no conflict currently. And we're going to end up in our final states, fail as before, or if it's satisfiable, we should get to this MG, where M satisfies G, and the conflict tuple should be empty. There should be no conflict. Okay, so the key idea here, we'll go slowly through this slide because this actually captures an idea that took me like months to learn the first time I learned it. So we'll see if we can get it in one slide. If we can, this has to do with the brilliance of the calculus, which this is Cesare Tonelli's calculus, and he did a really nice job with this. All right, so we're going to replace backtrack with 3 rules, and this is how it works. So first of all, as soon as you identify a conflict, so you're going down, you've built your trail, you've got some decisions maybe, and suddenly one of your clauses becomes false, okay? All the literals in that clause are false. You got to do something. You got to backtrack. But instead of backtracking, we're going to do this. First thing we do is we just say, oh, whatever clause is false, I'm going to copy that clause into that C slot, okay? So I just take this L1 through Ln and put it into that C, okay? So far, so good, right? That's not hard. I just bookkeeped the reason that I'm in a conflict. Now, here's where it gets clever. It turns out that I have enough information to know why I got into a conflict. Why did I get into that conflict? Well, I can look back at the trail and see which was the most recent literal in my clause that got set, right? Before that, things were great. I still had hope. I had at least one literal left that could have been true, but somebody set it to false. Who did it? Well, it was probably, or rather, it has to have been from a propagate step. Okay, because as soon as I get to all but one, propagate's going to kick in. But if there are 2 clauses like that, and I propagate one of them, then it gets to this one before I can propagate it and makes it false. That's how this can happen. So some propagation forced that last literal to be false. So what I can do is I can say, look, there's some literal in the conflict called L, which appears most recently in the trail. That's what this notation means. This less than M means L occurs before L prime. So all the other literals occurred before this L, okay? And that's the last one in C. Furthermore, there's another clause somewhere. Sorry. Yeah, this doesn't say anything about D. Let's see. Huh, hadn't thought about that before. I think it does have to be the most recent one in C. But what this is actually saying is it's the most recent one in whatever clause propagated most recently, right? In any case, you take this literal that made C false, and then what you do is you look at which clause propagated that literal. That's what this one is. And then you do a Boolean resolution step on the 2 clauses, okay? What does that mean? Well, it just means I take every literal in C except for the one that got propagated, and every literal in the propagating clause except the one it propagated, and I create a new clause out of those literals. Now, a fundamental truth about Boolean reasoning is if I have a clause with a variable that appears over here like x, and another clause with where variable appears not x, then it is always the case that this implies the clause that where I combine the two together and remove the x's. That's called Boolean resolution, and that's exactly what we're doing here. So this new clause C is actually implied by two of the other clauses in my formula. Okay, so it has to be the case that if there's a solution for the original clauses, that solution also has to satisfy this new clause. Okay, so why is this helpful? Well, basically now that I have this new C clause, I can keep trying to apply explain, right? I can say, well, what was the other most recent literal that got set? What was the other most recent literal? And keep doing that until the literal that I got set that basically there are no more literals in the current decision level in C. That's where we need to get to. So then once I get there, I can apply the back jump rule. So let's see what the back jump rule looks like. Back jump rule says, all right, you've got a clause in your conflict slot. It's got some literals in it. And we have this interesting property, which is the level of the literals of all but the most recent literal all have to be above some level. Okay, now if you think about it, this takes a little bit of thought, but if you think about this trail, right? You got this trail, decision, you got some propagations, decision, and so on. If you look at the most recent part of the trail, there's maybe some propagations there. Some of those propagations caused your conflict. You explain away all of those propagations. Now there's no more literals in your conflict from the most recent part of the trail. So where are the literals in your conflict from? Well, they could be from all sorts of places earlier on the trail, right? So what we're going to do is we're going to say one of those literals has to still be from the current decision level. Otherwise, it would have been a conflict earlier. But all the other literals can come from somewhere earlier. In fact, what we're going to do is we're going to look to see what level is the second most recent literal from. And we're going to jump all the way back to there because we can. And that lets us sort of skip over a bunch of stuff that might not be relevant. Now, Mate is going to tell me, yeah, but chronological backtracking works well in some cases. Okay, forget about that. This works well in some cases, not always. But it's a clever idea. So let's just understand it. Okay. Basically, what we're going to do is maintain this invariant that whatever's in the conflict slot is entailed by the rest of the formula. And that's maintained because resolution preserves that. And the trail is always going to be enough to make the conflict clause false. That's right. That's right. It's a non-deterministic. You're right. So what this says is you've got the level of all the literals, and you can jump back to any spot between that level and the current level. Now, in practice, you may want to jump back as far as you can, right? Okay, so we're going to look at an example of how this works, and then I think it'll be time for lunch. Okay. So let's take this example. So here we have some formula F, and oh, it says my battery's almost dead. Is there a place I can plug in? Yeah, let me just do that real quick. Okay. All right, so here's a formula. I've got 1, 2, 3, 4, 5, 6 clauses. All right. Some of them are simple, some of them have a few variables in it. And let's just watch how the calculus or the transition system operates on this formula. So we start off, the trail is empty, we have everything in F, and we have no conflict, okay? And well, the first thing we can do is we can clearly propagate that first clause. The first clause just has a single variable in it, number 1. So we better set 1 to true. So we set 1 to true by putting it in the trail. So far, so good. Now, notice that if 1 is true, then the second clause now can trigger propagate because 2 has to be true. So we can do that as well. And then, well, we don't have any more propagations. So we better make a decision. Let's say we set 3 to true. Why not? Well, if we set 3 to true, now the third clause propagates. We can set 4 to true. Let's make another decision. Let's say we set 5 to true. We do another propagation, set 6 to false. And then let's see. Now we've got 2 is true, 5 is true, 6 is false. So we can propagate that 7 is true. But now look. We've got 5 is true. Sorry. We can propagate the 7 is true based on this fifth clause here. Right, because 1 is true and 5 is true. So 7 better be true. And now notice that this last clause is in conflict, right? Because 2 is true, 5 is true, 6 is false, 7 is true. Okay, so we're going to take that last clause and we're going to put it in our conflict slot. Okay? Great. Now let's think about why did this happen to us? Well, the last thing that happened was that 7 got set to true. It got set by that next to the last clause. So if we explain with that clause, then basically 7 becomes our variable that we use in resolution. And so if we take this clause and resolve it with this clause around 7, that just means we get rid of the 7 and copy the rest down. So we have, this should be a not 1. Okay, that should be a not 1. So we have not 1, not 2, not 5, and 6. Okay? All right, so we still have, this is still in conflict, right? This clause, but it got rid of the 7. So where did this, how come this clause is in conflict? Well, now we can look at the 6. So the 6 got propagated by the not 5 or not 6. Again, this should be a -1, not 1. So our new conflict is not 1 or not 2 or not 5. Okay, now notice that the most recent literal is a decision, that not 5, right? 5 was set as a decision. And the other literals are all in earlier decision levels. So that's exactly what we need to apply back jump. And if we ignore the most recent literal 5, the other literals are all the way back at decision level 0, right? That means we can back jump all the way back to where 1 and 2 were the only things on the trail and set 5 to be false all the way back there. Okay? So that's the key idea behind non-chronological back jumping. You basically take the clause in conflict, do a series of resolution steps until all but the last literal are in earlier decision levels, and then you can jump all the way back to the decision level of those earlier literals. All right. Good. So I think we'll stop there for lunch. And I'll put this back up in case you want to get started on getting CVC5 set up.
Okay, so I think it's better to get that started because if you're compiling, it takes some time. So we'll reconvene back at, what does the schedule say? 2 o'clock?
to the
To the
lab. This page is directly linked from the program.
Okay.
Scroll down.
Okay, so we'll meet here back at 2 o'clock, and there is a link to the GitHub page that Clark showed at the bottom of the schedule for the winter school page. Okay, thanks, Clark. So lunch is in the same place where we had coffee. Okay, so welcome back after lunch. We'll have the second lecture session by Clark, and then we'll have the hands-on session. So there are some instructions about the installation that Clark is going to mention.
Okay, I just wanted to tell you a couple of details about this installation procedure here. So you can see some instructions for configuring CVC5. If you're on Mac OS, then this is the right set of instructions. I'm not sure Mac OS will work. Okay, so under this, there's some additional information about configuring with ASAN and UBSAN, which are additional debugging aids. I don't know for sure if those work on Mac, unfortunately. For Linux, though, you actually don't need, you can have it, but you don't need this static flag for Linux, and it'll actually compile a bit faster if you do that. Furthermore, I think you have to delete the static flag if you want to use the UBSAN or ASAN. Okay. So anyway, if you're just doing regular building, what I have there works. If you want to build on Linux and you want to go faster, get rid of the static flag. And if you want to use UBSAN or ASAN, also get rid of the static flag. All right. Okay. So back to our transition system calculus. And look, the slides have magically fixed themselves, so there's no typo in the slide anymore. All right, so this is the calculus for CDCL. So it has propagate, decide, and then instead of just this one back jump rule, it has conflict explain and the special back jump rule that lets you back jump more than one decision at a time. Now, you can do more. So here's a few more rules that actually represent things that are really done in SAT solvers. And the first one is called learn. And this just says that if there's ever a clause that follows from the formula that you have, you can go ahead and add that clause to your formula. And in fact, there are lots of different heuristics for what kinds of clauses you might want to add to your formula at what times. And I'm not going to go into all of that, but there is one place where it makes a lot of sense to add something. And that is, once you get your conflict that you're about to back jump on, an easy way to make that work is just to go ahead and add that conflict clause to the formula. And then actually the CDCL algorithm will automatically jump to the right place and do the propagation for you. So going from this sort of line here to this line here, one way to implement that is just to take this conflict clause and add it to F. So that's something that we'll typically do. We'll use this learn rule to add that conflict clause to F. And then when we back jump, the propagation is handled automatically. Yeah.
Are you assuming the priority in these rules? Like if there are multiple rules that can be applied, then this will be applied before?
Yeah, great question. So right now, we're not talking about that, but that's typically when you have a set of rules like this, that's a question about strategy, right? So a strategy is basically a function that tells you which rule to apply next. And I will talk about strategies in a bit. Okay, so learn just means you can add clauses to your formula. Now, the tricky thing is you want to learn clauses that are useful, but you don't want to learn too many because then your set of clauses gets too big and it slows everything down. So there's this sort of interesting balancing act. And again, I'm not going to go into the details. This is like, you know, many PhDs worth of research to figure out when do you learn and when do you forget clauses. But sometimes you figure out that some clauses that you learned were just not very helpful, and you kick them out of your set of clauses. And that's what the forget rule is for. And you can do it as long as the clause is redundant in some sense. It's not adding any new information. Certainly anything that you learned with the learn rule can later be forgotten, and that's okay. And then finally, there's this restart rule. And that just says, well, if you like, you can just throw away your whole trail and start over. Why not? That seems, it's actually a much better idea than it sounds like. And the reason is because if you're really good at learning clauses, then that's really where the heart of your work has gone, is into learning the right clauses. And it may be that you've built a trail that's going all the way down into some, deep, dark corner and not being very useful, but you learned a bunch of good clauses on the way. So then what you're going to do is just restart. And now that you've learned those clauses, it may direct you in a different direction. In fact, modern CDCL solvers, how often do you think they restart? Yeah, multiple times per second. They're just restarting all the time. And this turns out to be the right thing to do. So essentially, you shouldn't think about a modern SAT solver as exploring a tree. That's not really what it does. What it does is it charges off, learns a bunch of clauses, restarts, charges off, learns a bunch of clauses, restarts, learns a bunch of clauses, restarts. And what happens is as it does these probes learning clauses, the probes get shallower and shallower and shallower, and eventually, somehow, magically, it's learned everything it needs and it's done. But this idea of like going down and exploring a search tree, we don't do that at all. So it's kind of interesting. Okay. All right. So then at the core, you have these rules in modern CDCL solver. And then we can say, well, the basic rules are just propagate, decide, conflict, explain, and back jump. And then the sort of extended one also adds learn, forget, and restart. And why is that important? Well, it turns out that for the basic rules, no matter how you apply the rules, it's always a finite derivation. You basically at some point run out of things to do. And that's because there's only a finite number of possible trails that can be generated. And you can kind of show that every step is making progress towards generating another trail. So that's kind of nice. And right, you also know that in fact, so an exhausted execution is one where you can't apply any more rules. And you can also show that basically when you've reached an exhausted execution, you're either in the fail state or there's no conflict. And in fact, you can show that if you end with fail, then it really is unsatisfiable. So you can prove that. And you can also prove that if you're in an exhausted execution, no rules apply, then actually it was satisfiable. Okay, so the calculus has sort of all the nice properties you'd like it to have. You can show that it terminates for the core set of rules. You can show that it's sound. It always gives you, if it says unsat, it really is unsat. And it's complete, meaning that if it stops, then you actually have a satisfiable result. Okay, so that's great. All right, so now we're going to talk about strategies. So this is to your question. So, yes.
Basically, it can include the conflict and.
Yes. Yes, it includes propagate, decide, and the conflict explain back jump. Yeah, those 5. You can see that if you added learn, forget, and restart, that now it doesn't have termination anymore, right? Because you can just keep restarting. Okay, so notice that as long as you apply a basic rule between every 2 learns, and you don't apply restart too many times, you still get you can still get termination even in the case of with the extended rules. But what should be your strategy? How should you apply these? So here's a common strategy. Basically, you count how many conflicts are going on, and if you reach some number, you apply restart. Okay. If you have a false clause, then you better do conflict analysis. So you apply conflict. And as long as you can apply explain and backjump, keep doing that. Apply learn to learn the clause that you're going to use to backjump. Then you backjump, apply propagate as much as you can, and then decide. So notice that making a decision is the thing you want to do last, because an application of the decision rule is an exponential step. It's splitting, it's basically, you know, in the worst case, giving you exponential behavior in your search. So you do everything you can think of besides that. And then in the end, if you have nothing else to do, you make a decision. Okay. And this is what, you know, real SAT solvers actually do. All right. Any questions on DPLL? It seems that way, but basically it means you should do conflict resolution before propagation. Because if you're in a conflict state, there's no point in propagating. You want to backjump. But as soon as you backjumped, you immediately do propagation. Yeah.
When you say apply backjump in step 5, you really mean that keep applying your explain until backjump is effective or something?
Right. So basically this 2 through 5, you only do if there's a conflict. So you can think of it this way, you know, you're in some state. If you can do conflict analysis, you do steps 2 through 5 until you can't do any more conflict analysis. And then the sort of normal case is you do propagate, decide, and then occasionally restart. Or maybe not so occasionally, maybe very frequently. Right. So let's see. I guess you can have a chain of back jumps, but I think you might have to have a propagate in between. So you would do explain, back jump creates a new, when you back jump, you add a literal to the trail. So that could have an effect. It could do some more propagations. And then you would do some more back jumping. So you can certainly have like a chain reaction of back jumps. But you might, I think you might have a propagate in between. Yeah. So the conflict you were working with gets resolved, but you might create a new conflict by propagating. That's right. Yeah. Yes. Yes. That's right. Yeah, that's so this is a convenient, this is another trick in SAT solvers. You need some kind of counter to know like how long it's been since you last did something. The number of conflicts is a nice deterministic counter, because if you run the same algorithm, then you'll get the same conflicts every time. So rather than, you know, waiting for 5 seconds, which, you know, could be non-deterministic, you count conflicts, and that makes the whole algorithm deterministic. Okay. Any more questions on the just DPLL and CDCL? Yeah. So that's just, so actually it's a little bit of a lie. So in practice, I'm not sure SAT solvers actually do that, because they don't actually care about termination, like guaranteed termination. But this is to get termination. So if you want to ensure that you'll eventually terminate, then you keep increasing that number, and that way you'll eventually, you have a guarantee of termination. Theoretical guarantee. Yes. No, not really. They both have, well, as long as P doesn't equal NP, their complexity is exponential. And the best known bounds on the algorithms are like what is it? It's like, I don't know. Do you know this? It's like 2 to the n over something, something. But yeah, all known bounds are exponential. It's better than 2 to the n, yes. There are provable bounds better than 2 to the n, but they're all exponential. Yeah. And the bounds that we know in theory have very little to do with what actually happens in practice, unfortunately. So what works in practice is just all sorts of crazy, super fast engineering here and heuristics. And that's, in fact, another fun story. Were you there for this? Were you at UCLA? Mate. Anyway, oh, Kuldeep, you were there. Anyway, Karam Sakala got up and he admonished this group of researchers and said, you aren't doing science. You're just like, throwing darts at a board because there's this big, gap between the theory and the sort of people writing solvers. So, he was being provocative and he got a good response out of the room. But there's like a good point there, right? Is like, how come like you asked this question, what is the complexity bound on CDCL? Who knows? Like there's so many bells and whistles in there that no theoretician will go near it, right? So it's a good question. All right. Other questions? Okay, so now that we have this nice abstract calculus for describing how to solve SAT, how can we build on it to solve SMT? So it turns out that it's actually a pretty straightforward extension of the calculus we've just done. So the difference is that F is still going to be in CNF. It's still going to be a set of clauses. The clauses are going to be disjunctions of literals. The difference is that instead of a literal being a variable or the negation of a variable, a literal is a theory atom or the negation of a theory atom. Okay, that's it. Right, so now M is a sequence of these theory literals, and we're going to add a few rules. The rules look similar, but they have a T in front of them because they actually take into account the semantics of the theory. Yeah, I think I'll skip some of the technical details here. All right, so how's this going to work? All right, so here's the first important rule. This is basically another way to get a conflict. Once you lift things to the SMT level, there's 2 ways to get a conflict. So one is if you have a clause and all the literals in the clause are negated by the trail. Okay, that's the way we already had before. That gives you a conflict. But now we have another way to get a conflict, which is if the literals in the trail are deemed to be unsatisfiable in the theory, then the theory can raise up a red flag and say, nope, well, any subset of the current trail can be marked as a conflict, okay? So basically, if you think of it from the theory's point of view, the SAT solver is going along, making decisions or propagations, assigning values to these theory atoms, and theory is watching. And if at some point you've assigned a bunch of stuff, the theory can say, stop, here's a subset of the things you've assigned that is inconsistent in the theory, okay? That's called a T conflict. This symbol.
Second one, the N derives.
Oh, sorry. Yeah. So good. So we use this turnstile symbol to mean logical entailment. And previously we were using it always to mean propositional entailment. But now we're going to talk about 2 different kinds. So P means propositional and T means in the theory. So if it has a subscript T, it means you need the theory semantics to derive the contradiction. And P means you just need propositional reasoning to derive the contradiction.
P means both P and P or just P?
I guess both, yeah. Okay. Good. So what's cool is if the theory figures out a conflict, it just drops it into that C component of the state, just the same way as the SAT solver did when it derived a conflict, and everything just works. All right, so that's kind of cool. Great, we also have a theory analog of propagation. And this just says, if I have any literal that's known, and the theory can figure out that that literal has to be true, then the theory can actually go ahead and add that to the trail. So this might be a case where, let's say I asserted x equals y, right? And somewhere in my formula, I also have the literal x is less than y. So from the SAT solver's point of view, those are just two different variables, so it doesn't know anything about them. But the theory says, oh, if x is equal to y, then certainly it's not the case that x is less than y, and it can just go ahead and set that literal to false. Okay, so that's T propagate. All right, and then we have this interesting version of explain that's a T explain. Why do you need a T explain? Well, remember, when we're doing conflict analysis, right? We look at some conflict and we say, oh, there's some literal that was the last literal that got set. I need to know why that is. And before, we could always point to some application of propagate that set that literal. But notice that with T propagate, it could be that the literal in my conflict clause was actually set by T propagate, not by propagate, right? So if that's the case, then we have to call T explain. And what T explain does is it just notice that in T propagate, T knows that some subset of M entails L, but it doesn't tell the SAT solver which subset it is. So when you ask for an explanation, you have to go back and say, oh, which subset of M was it that implied L? And let's go ahead and turn and pretend that was a clause, right? All right, let me just break this down a little bit. One way to think about it is the theory knows that L1 and L2 implies L3, let's say, right? The SAT solver doesn't know that. Well, one way to tell the SAT solver that is to add the clause, not L1 or not L2 or L3. But adding clauses to the SAT solver can be an expensive thing to do. And often the theory propagations don't really help, right? So what you want to do is you want to do the theory propagation, but you don't want to go to the trouble of adding the clause unless you really have to. And when you have to is when the explanation procedure asks for it. So this is actually quite a clever optimization, because the obvious thing to do is just, when you do theory propagation, just add the clause. But it turns out to be quite a bit more efficient to just set the value and then only if asked for to add the clause. Okay? All these. When? If the literal shows up in a conflict and you're trying to explain that literal. Yeah.
And say L comma L prime L negation of L. Is that what it means?
Yeah, it means neither L nor the negation of L is already in the trail.
How can both L and its negation be in the trail?
No, neither one is in the trail. Yeah. Yeah. Good point. You should never have both L and its negation in the trail. That would be bad. All right, good. So now with this, now we can model lots of different ways of having the SAT solver talk to the theory solver. So let's look at how that works. Okay, so remember this example where we just have these 4 atoms. And remember, we had a naive way, the very lazy way. So let's look at the very lazy way now in the calculus. So we start out with just 3 clauses. We can immediately apply propagate to 2 of the clauses because they're already unit clauses. They just have one literal. So 1 and 4, 1 and negation of 4 get propagated. Now, that's okay. So now we can't do any more propagate, so we'll do a decision. Let's say we decide 2 to be false. Well, one and let's see. So if once we decide that, we actually have an assignment, or we have a satisfying assignment in the SAT world. So we can go ahead and call the theory solver. The theory solver says, no, that's no good. And it just gives back this not 1 or 2 or 4, which is the negation of the entire trail as a conflict. So we're going to go ahead and learn that, add it to the set of formulas, and then we're just going to restart. Well, restart and propagate. But now, once we propagate, we can go ahead and propagate 2 and 3, because once 1 is 2, 4 is false, then that forces 2 to be true, 2 forces 3 to be true. So now we have another satisfying assignment. We give it to the theory solver says no, we learn a conflict, and let's see. Right, so actually this should maybe be 1, 4, 2, 3, but it's okay. These are actually the ones that contribute to the conflict. And then we already fail. Okay, so we're going to show how we can do this. This is still not being very smart about things, so we're going to show you how we can do this more smart. Okay, so the first thing we're going to do is we're going to make the SAT solver online, which means we can do these theory propagations and send stuff right into the SAT solver. We can also send conflicts to the SAT solver while it's in the middle of doing stuff. We also have an incremental and explicating T solver, which means it can check on the fly as you go, and it can also identify small subsets of the trail that are unsatisfiable. So now let's see what happens. All right, so we start out as before. We make this decision. But now we see this conflict, and notice that we know that the theory solver is smart enough to see that 1 and 2 are already in conflict, right? It doesn't need 4, so it doesn't include 4 as part of the conflict. So now we can back jump, propagate, again, get a conflict, and fail. Okay, so this was a little bit faster. Let's see. Right, but we can and we can do a little bit better. But let's go ahead and look at the strategy for this approach. So basically what you're going to do is, again, apply conflict if you can at the propositional level. Ask the theory, see if theory can apply T conflict. If any one of those happens, then you do explain, learn, back jump. Otherwise, propagate and decide. Okay. Now notice that step 2, this is again where a heuristic comes into play, because you don't actually have to do step 2 unless you have a full assignment in the SAT solver. If you have a partial assignment, then what you might want to do is do some quick checks to see if it's T unsatisfiable, whatever can be done quickly, and then leave any kind of really hard stuff until, maybe the SAT solver is done. In fact, this is exactly what we do in CVC5. So in CVC5, every time you do some propagation at the SAT level, we call back to the theory solver, but we distinguish cases. We have what's called a standard check, and we have what's called a full check. So a standard check, you do every time. And when a theory gets a standard check, it basically does whatever it can do very cheap, because this is going to happen a lot. And it just does really cheap checks for conflicts. When it gets a full check, then it has to do everything. It basically has to give a guarantee that it's done. Okay. Now, yeah? Yeah, I think this means both explain, learn, and T-explain and T-learn. It's just lumping everything here together. Basically, if you get a conflict, then you either have to use explain or T-explain to unwind the conflict. So I haven't talked about T-propagate yet. Yeah, we're going to add that next. Okay. So with t-propagate and t-explain, we can also guide the search. Okay, so let's see how that works. So same example. We do 1 and not 4 by propagate. But now notice that if 1 is true and 4 is false, we can actually, even just 1 by itself implies that 2 has to be true, right? In the theory, 1 implies 2. So if 2 arguments of the function are equal, the functions have to be equal. So because 1 implies 2, I can t-propagate 2, right? Furthermore, 1 and not 4 entails in the theory that 3 has to be false. Because if 1 and 3 imply 4, then 1 and not 4 implies not 3. Okay? And then boom, we got a conflict. All right, so notice that if we're willing to have the theory be quite proactive, we can actually solve this problem with no decisions at all. Right? The theory just is pushing information as soon as it gets it, and it's enough to create the conflict already. Okay, so in practice, this is exactly what we try to do. We try to, well, yeah, I think the next slide is about strategy. Right, so a modern lazy SMT solver has the core DPLL rules plus t-conflict, t-propagate, and t-explain. Those are the basic DPL modulo theories rules. And then it also can do learn, forget, and restart, same as with the propositional level. And I guess, do we have, yeah, so this strategy should really be updated to do t-propagate at the same time as propagate. Right, so you want to propagate as much as you can at the Boolean level, then you want to propagate as much as you can at the theory level, and get as many literals assigned as possible before you decide. Okay. What about the correctness of the DPLLT? Well, same things apply here. So let's see. Okay, so first of all, just for basic DPLL, we can say a little bit more now, which is if you apply learn and forget only a finite number of times and restart with increased periodicity, then you get termination. Yeah, and every exhausted execution ends with either no conflict or an unsatisfiable result. Just as with the basic one, we have soundness and completeness, so this is great. And yeah, so that's basically it for the abstract DPLL T or DPLL modulo theories calculus. It was right here. So it's the same. Well, let's see. Yeah, it's the same. So as long as you apply learn and forget finitely many times and restart with increased periodicity, you still have termination. As long as your theory is decidable. Yeah, the theory check has to be decidable because, well, let's see. Yeah, because otherwise, you know, that step could fail. Yeah. Okay. What's that? This is, you know, just heuristics that are built into the solver. So in practice, yeah, good question. So in practice, what you do is you apply learn every time you do a back jump. And then periodically, after a certain number of conflicts, you look at everything you've learned and you say, I've learned too many things, and you just throw away some of them according to some heuristic. Yeah, that's how it's done in practice. And of course, there are lots of other tricks you can do to learn things heuristically on the way that are theory specific, or yeah, we'll look at some of that. I think I'm going to skip this and go to here. All right. Yeah.
Simplification isn't very obvious, so as long as the line individual theories that decide to do this is going to turn out for a problem.
Well, one way to think about it is you can always run the SAT solver to completion, take the model, ask the theory, is this consistent? It says yes or no. As long as it's decidable, it can say that. Yeah, you can always do that. So you get everything else is an optimization on top of that. Yeah. Okay. Now, I'm going to talk about something called splitting on demand. So this is something that's used in pretty much every modern SMT solver, and it's not yet modeled by this calculus. So here's the observation. For some theories, let's say you get some set of literals from the SAT solver, hand it off to the theory and say, is this set of literals consistent? For some theories, answering that question requires reasoning by cases, okay? It can't just look at, even though it only got a conjunction, right? It didn't get any disjunctions or any Boolean operators, it still has to reason by cases. Let's see why that might be the case. Let's look at the theory of arrays. So let's say it has these two literals. So here R just means read, W means write. All right, so here we say read of write, where I and J, so you wrote at I, you read at J. Here you write at I and read at J, okay? We don't know whether reading at this J is equal to X unless we know whether I equals J. Okay, so we have to do some reasoning by cases. We say, all right, let's take the case where I is equal to J. Then that means that this thing reduces to X on the left-hand side. So that means there's a contradiction on this side. On the other hand, let's suppose that I is not equal to J. Then we get a contradiction over here, because if you read at A with I not equal to J, you'll just get read of AJ. And these two should be equal. Okay? So it turns out that this is unsatisfiable, but there's not an obvious way to just look at it and see that without considering some cases. And this is actually pretty typical. So a theory, the complexity of answering the query of just a conjunction of literals in a theory can vary. It could be linear, it could be polynomial, it could be exponential, it could be piece-based, right? So if it's one of these like exponential ones, probably you're going to have to do a whole search tree just to figure out if that conjunction of literals is satisfiable. And this is not great, because this means now you've got case splitting happening in two places. You've got case splitting going on in the SAT solver, and you've got case splitting going on in the theory solver. And maybe, you know, they're using different heuristics and they're competing with each other, and this is maybe not so great. So the alternative is, well, let's just put all the case splitting in one place. Okay, let's let the SAT solver do all of the case splitting. And the way we're going to do it is whenever we get to a point in the theory solver where we need to do case reasoning, we're just going to apply a learn step to move all of that over into the SAT solver. So why is this maybe a good idea? Well, like I said, all the case splitting happens in one place. We only have to implement case splitting infrastructure in one place. This is actually a big one if you're an implementer, right? And we're going to allow ourselves to learn more kinds of things. So what would we do? So again, suppose we get we're talking about the theory of arrays, and we see a constraint that looks like this. And then we get this question, is this satisfiable? So what we can do now is, instead of saying yes or no, we can say, well, I'm not sure, but it would greatly help me if you would please consider the following case analysis. So basically it says either, let's see. Right, I know that if S equals S prime, which is what this literal says, and if I equals J, then I know that S equals T. I also know that if S equals S prime and I is not equal to J, then S equals read of AJ. Okay, so basically I know these two facts. This is the case split, and I'm just going to send these two facts back as theory lemmas to the SAT solver. Okay, so now we have a slightly more general version of the learn rule. So basically what this says, this is going to let us do a few things. It's actually going to let us introduce new variables even, if that's helpful. So what it says is I can learn a new clause if the existential closure of that clause is entailed by everything I already know. And in particular, if the existential closure of that clause is a valid formula in the theory, which it is in this case, then I can learn that. What? Good. So it just, so these, remember these L1 through Ln, these are theory atoms or theory literals. So that means they say they like have some variables in them, you know, X less than Y, read of A, J, something, right? So what I'm saying is I could actually create new variables and put them in there. And then this just means that the formula, let's say I create a new variable X. X doesn't appear anywhere yet. If there exists X, and then the disjunction of those literals is a valid formula, then it's okay to do that. Let me give you an example of when you might want to do that. Suppose I have A not equal to B and A and B are arrays. Okay, I can say, oh, I'd actually like to conclude from that read of A at some index K is different from read of B at some index K. Now, it is actually true that there exists some K for which there is that difference. So I can actually just send that back as a lemma, that those two things are different and that it works. So you can prove that this is all okay. All right, now there's this other little condition here that says these literals have to be in some finite set. Now, this is again for termination. So it just means that if you're going to do this kind of learning where I'm conjuring up new literals, there better be some limit to how many things I can conjure, right? I can't just keep throwing lemmas and never stopping. So this is one way to ensure that I eventually stop. I know that every literal I'm conjuring up comes from some finite set, and often I can sort of figure out what that set is. There may be other methods, but you want to make sure that that doesn't go on forever. Yeah. That's right. Yeah. And basically what you can do is you can say, here's my theory, here's all the situations under which I might need to do a case split. And if you can prove that there's only a finite number of things you might ever split on, that gives you that set LS. Yeah. And this is true, for example, for the theory of arrays, because typically what happens is if you look at your whole formula and you look at all of the indexes into arrays that are used anywhere, then essentially all the combinations of equalities and disequalities between those indexes is everything you might want to split on. They can be infinite. Yeah, the size of the array is determined by the type of the index variable. So if the index variable is an integer, let's say, then it's infinite. Yeah. Okay. Right, so now we can relax this requirement that says, before we said, once you have a complete assignment, then we either have to check then we have to check whether M is satisfiable or not. Now we can say either we come back with a definitive answer whether M is satisfiable or not, or we generate a theory lemma. And if we generate a theory lemma, then we don't have to answer that question. And only if we've sort of used up all the literals in LS, then we have to answer the question. Okay. Let's look at an example of this. So here's an example using the theory of finite sets. So here we have, the usual operations on sets: union, intersection, empty set, membership. And our formula just says that X is equal to Y union Z. Y is not the empty set, and X is not equal to Z. Okay? So two clauses, right? The first is a unit clause. The second clause has two literals. So the first thing we're going to do is go ahead and propagate that first clause, that first literal, because it's in, this is a clause by itself. So great. Now let's say we make a decision. Let's go ahead and decide that Y is equal to the empty set. Okay, so we're going to decide that that literal is false, Y not equal to empty set. All right. Now we can propagate that X has to be not equal to Z by this clause. So far, so good. But now this is interesting. So we've actually satisfied the propositional part, which means now we need a definitive answer from the theory solver. Is this satisfiable or not? And the theory solver sees that X and Z, which are sets, are different, okay? But it doesn't really quite know what to do next. So it might do something like this. It might say, oh, well, if X and Z are different, then either there's an element in X that's not in Z, or there's an element in Z that's not in X. That's a reasonable case analysis to do. And so, so in fact, we can do that by learning this clause. So this clause, one way to read it is that if X is not equal to Z, that implies that either E is in X or E is in Z, where E is some new variable. So basically it's saying there exists some new variable E that's either in X or Z and is not in X or not in Z. That's just one way of saying there's some element that's in one but not the other. Okay? And E is a new variable. We just made it up. But because the existential closure of those two clauses is true, we can actually learn this by the t-learn rule. Okay? So now once we've learned this, now there's more we can do at the sat level. So now we say, okay, good. I already know that X is not equal to Z. So let me go ahead and pick one of these. Let's go ahead and pick the case where E is an element of X. Okay? So you make a decision. E is an element of X. Which means because E is an element of X, this is now false, so it must be the case that E is not an element of Z. All right, now, notice that once we've identified that there's an element that's in X that's not in Z, we can do a bit more deduction. So we can say, oh, well, if E is in X and X is equal to Y union Z, then that means, and I know that E is not in Z. That means that E has to be in Y. But Y is equal to the empty set, therefore E is in the empty set, therefore contradiction. So just by a chain of reasoning now in the set theory without doing any case analysis, we can arrive at a contradiction. So we can go ahead and do a t-conflict clause with these literals. So knowing that X equals Y union Z, that E is not in Z, that E is in X, and that Y is the empty set, that gives us this conflict. Okay, So any questions on this example? Yeah. Right. So that's where this little requirement comes in right here. So there's some finite set of literals that's all the things you could ever use. So in this case, E in X and E not in X and E in Y and E not in Y, those are elements of this finite set. And in general, for let's say for the theory of sets, maybe for every possible disequality between two sets, so let's say I have 10 set variables in my formula, then there's like, 45 possible ways of comparing two variables. For each one of those, you might introduce a new element, but that's all. So we know that there's only 45 possible things to do. Yeah. Now, again, in practice, we don't worry about this too much. We don't actually compute this set LS or worry about computing it, but we do worry about making sure that we don't do some infinite set of lemmas. Yeah. And you actually have to, when we come up with a new decision procedure for a new theory, we actually will do that proof to show that we can't do that infinite number of times.
Understand why X either X is not, if X is not equal to Z, then E should either belong to X or E should belong to Z.
Yeah, it's just this is okay. So this what I did here is I took the intuitive way of writing it and I twisted it around to make it a clause. So the intuitive way is to say E is in X and E is not in Z, or E is in Z and E is not in X, right? But that's not a clause, and we can only, everything has to be in CNF. So if you do some magic with distributivity, you get this instead. And it's equivalent, right? So it just says E is either in X or it's in Z, and also E is not in X or it's not in Z. And if you think about it, if you have one, then it forces it to not be in the other. Yeah. Just to make you think hard, basically. All right. So it turns out we can preserve all of the correctness. We still can have soundness, completeness, and termination. All right. Let's see. How are we doing on time? All right. Still got 30 minutes. Good. Okay. So, yeah, go ahead.
Share some more examples of such learning. So I gathered you said for arrays you look at equalities and disequalities of the indices.
Yes.
For sets you look at membership of an arbitrary variable.
Yeah. Mm-hmm.
What some other examples?
Yeah. Good. Let me give you a general idea of when this comes into play. So when we write a new decision procedure for a particular theory, typically what we'll do is write a bunch of rules, okay, and show that if you apply all these rules to saturation, then you'll be able to decide whether it's satisfiable or not. If these rules have branching, if there are branching rules, any place there's a branching rule, that's where you want to do something like this. So arrays was an example, sets is an example. Another example is, let's say you have the theory of integers, and you know that x1 is less than or equal to x is less than or equal to 2, right? Then I can deduce that x is either equal to 1 or it's equal to 2, but I actually have to do that branch. I have to try both cases. And so we would actually, with some heuristics, when we get into a case like that in integers, we'd actually generate all the possible cases and say, look, it's either 1 or it's 2. So anytime you have that kind of case analysis going on, you can do this.
I'm very curious about the array example that you gave where you say equality and disequality of indices. Is that are there any completeness guarantees associated with it that if you do that, then you're sorted with arrays and you will never have to come back to the theory solver?
Yes. Well, let's see. No. So typically what happens is you go down some particular branch of the SAT search, and then you get a particular set of literals. And for that particular set of literals, you can do the theory lemmas and then send them back to the SAT solver. And then you know that on that branch, you're sort of sorted. But now you might backtrack and go down a different branch, and then you might have to generate a bunch of new lemmas. Yeah.
Sorry, pressing on, but just my question was slightly different. I'm asking the question whether if, this equality of indices, is there a complete strategy for being equality and disequality? Is that a complete strategy for arrays? Or
It is. So if you know all of the indices, whether they're equal or disequal,
yes,
then all of those, then the axiom schema, you can always instantiate it to a set of deductions. So basically, you know whether something is true or not. Yeah, you can just sort of simplify everything that way. Yeah. Yeah, good question. Yes. Oh, I can't hear you. Thank you.
Yeah, in the event when there was this situation where these two sets were different, this introduction of this variable E, which kind of witnesses the difference between the
Yes.
two sets, is this like, I mean, this is an inference that the theory that the underlying theory should be able to do, that if you're given these two variables x not equal to y, then the underlying theory would instantiate or kind of witness this difference. So is it the case that the theory is doing this, or is it the case that you have added an explicit rule saying that introduce this variable? This is just the theory which should do this ideally, right?
Yeah, so actually both things that you said are true. So what happens is we have some set of rules inside the theory solver that we're using to figure out whether the theory literals are consistent. And those rules are the ones that would generate this. Okay, so they're different from our abstract DPLL rules that are governing the whole structure of things. But this is like within a theory. I haven't gone into too much detail, right? I showed you the example of IDL, how we solve that. But in general, to solve the theory, we typically have another whole set of rules. And those rules are the ones that could generate this kind of thing. Yeah. Yeah. Specifically, whenever I have a rule that does some kind of case analysis, or a rule that derives some, well, there exists an X such that whatever, then we would apply those to introduce new variables and introduce new lemmas. Yep. All right, so I want to talk a little bit about combining theories. So remember when I showed you this diagram at the beginning, there's the SAT solver, it talks to this core, and the core talks to all the different theories. So you might have this question, well, suppose that each of the theories says, good, my set of literals is good. How do you know that the whole thing is satisfiable? Is that enough? That's this question. All right, so let's say we have a formula that looks like this, right? It's combining arrays, uninterpreted functions, and arithmetic. And let's say we have theory solvers for each one of these things individually. Can we solve this problem, right? This problem is mixing them all up, right? Clearly I've got an array that's indexed by some integer, and I'm using some arithmetic to index into it. I've got uninterpreted functions also over integers. None of my theory solvers know how to solve this, right? How do I do it? Okay, so it turns out that there is a very nice classical result called the Nelson-Oppen theorem that shows you how to do this. Okay, so first of all, let's take a look at this simple example that's combining, let's say, linear real arithmetic with uninterpreted functions. So the first step is we've got to somehow make our literals only in one theory, because the theories only understand things in their own theory. So, but we can do this. So there's a step called purification, which is, or it's also called conversion to separate form. And it's very simple. We just introduce a variable whenever we have a term that mixes symbols from two theories. So if I have f applied to a subtraction, then I'm going to introduce a new variable for that subtraction and just say, oh, E1 is equal to this difference. But now I still have a mix, right? So what I'm going to do is I'm going to introduce E2 and E3, and I end up with 4 equations. But now notice each of the 4 equations uses symbols only from a single theory. All right. So that's great. That's pretty straightforward. Here's another example. And again, I just apply this purification process to get constraints that only have symbols from a single theory. And then the next step is once you've separated it, you send each set of constraints to its respective theory. You're not quite done. The theories have to talk to each other. And in particular, they have to talk to each other about equalities on shared variables, okay? Shared or interface. So these are called interface equalities. They're equalities between these shared, yeah, I'm calling them variables. You can also think of them as uninterpreted constants, same thing. So basically, if we look and see which of these variables appear in both columns, right? Well, E1, E2, E3, E4, E5, and A. So all 6 of these variables appear in both columns. So I need to know which of these variables are equal, okay? So luckily, I can do some deduction. So L1 looks and says, oh, actually, I know that E2 has to equal E3. Why is that? Well, because x equals y, which means f of x has to equal f of y, which means E2 has to equal E3. So it's going to go ahead and tell this to the other theory. Now notice if E2 equals E3, then E2 minus E3 is 0, which means E1 equals E4. So let's go ahead and tell that to the other theory. Great. Well, if E1 equals E4, now that means that A equals E5 based on these 2 equations. So we can go ahead and send it back. And now look, if A equals E5, that means A is greater than A plus 2, right? And in fact, that means it's unsatisfiable. All right. So we're getting a picture of how this might work. We want to convert to these separate forms, have each theory solver work on its own set of constraints, and theory solvers have this sort of shared language involving variables that appear in more than one of the theories, and they can tell each other about which of those are equal or not. And by doing that, they may be able to drive a contradiction. Now, if any theory at any point derives a contradiction, we know that the whole thing is unsatisfiable because every step we've taken is a sound deductive step. So that's great. Let's see. Let's have a look at this example. Now here we have integer arithmetic, not real arithmetic. We can do the same step. We purify the literals. We do all of this reasoning. This is similar to what was done before. But now notice that we have L1 knows something, but it doesn't know exactly the right thing. It can't just push an equality over. It knows that x is either equal to E1 or it's equal to E2, right? So x is between 1 and 2, x equals 1 or x equals 2. E1 is 1, E2 is 2. So it's equal to one of them, but we don't know which one, right? We again have this sort of case analysis problem. So it turns out that in order to make things work, you have to look at all these cases. So if I ignore this, right? If I just say, oh, I don't have anything to tell L2, the L2 is going to say, well, everything looks good to me. L1 is going to say, well, everything looks good to me. And they're going to both report satisfiable. But in fact, there's a hidden unsatisfiability here, because if I consider the case where x is 1, then that means x equals E1, which means B equals E4, which means, I don't know, more stuff goes on. You get a contradiction in both cases. Let's look at it. Let's consider each case. X equals E1. That means, I see. That means that A equals B, right, from the first two constraints. And once you send that back to L1, we've got A equals B plus 2 and A equals B, so we get a contradiction. And in the case where x equals E2, send that over here. That means, again, looking at this, that B equals E3. But if you send B equals E3 over here, let's see, why doesn't it like that? Oh. This is E3. A4 is, A is A4. Right. So B is, so then A plus 2 equals A plus 3, right? Yeah. So we get a contradiction. A minus 2, okay, right. Oh yeah, that's easier. You can actually get both. So, all right, good. Okay, so what you have to do, well, let's look at the, let's look at what you have to do. So basically, if we take this set C and call that the set, I'm going to call it the shared variables. It's also the set of constants. What? Convex? I'll come back to that in a second. Yeah, good question. All right, so here's the idea. If I'm given these two sets of constraints, L1 and L2, where each of them share some variables in C, and I want to know whether the whole thing is satisfiable or unsatisfiable, then first of all, I have to agree on an arrangement. An arrangement just means that I know for each pair of variables in C whether they're equal or disequal. Okay, now, if I'm lucky, like in that first example, and I can just push equalities back and forth, then I don't have to do any guessing. But if I'm unlucky, I might have to actually enumerate arrangements and try all of them. And what the Nelson-Oppen algorithm, or what that work showed, is that this is the kind of the hard work you have to do to make this theory combination work, is you have to get all of the theories to agree on this arrangement, okay? If anybody says unsatisfiable for that arrangement, then the thing is unsatisfiable. Sorry, this is a non-deterministic algorithm. Let me state it slightly differently. Loop over all possible arrangements. If there exists any arrangement for which all of the theories are satisfiable, then great, it's satisfiable. If the theories are unsatisfiable for every arrangement, then it's unsatisfiable. Okay. Now, in practice, do you actually want to loop over all the arrangements? How many arrangements are there on n variables? Anybody know? It's a fun number. It's the Bell number. And I think it grows something like 2 to the 2 to the n. It's not a happy number. So you don't really want to guess all the arrangements. So what do we do in practice? Well, in practice, we will propagate all the equalities that we can. And then we sort of have this implicit agreement, which is if there are two variables that are not known to be equal, then you better be okay with them being not equal, disequal. If you're not okay with that, you better generate a lemma or a k-split. That's kind of how we do it, right? So basically, what each theory solver has to do, it has to look at all of the shared variables it knows about, has to say, do I know if any of these are equal? If I do, I tell everybody. Whatever else is left, I kind of look at it, squint at it and say, would I be okay if these are all different? If I'm okay with that, then great, I don't have to do anything. If I'm not okay with that, I need to generate some kind of lemma or k-split to sort of get okay with that. And in practice, that actually works pretty well. All right, so I think this is captured by, oh, okay, okay, there's a calculus here for it, but first I have to tell you about some other stuff. Okay, so we'll get to that in a second. So this basic idea of iterate through arrangements, check, is terminating because there's a finite number of arrangements, even though there's a lot. It's sound and it's complete, which means this algorithm actually does give you a way to answer this theory combination question, which is great. As long as the theories are stably infinite. What does that mean? Okay, a theory is stably infinite if whenever you have a quantifier-free satisfiable formula, a quantifier-free formula that's satisfiable, it's also satisfiable in an infinite model. Okay, so without going into too many details, it just means that the domain of variables in the model that you come up with a solution has to be infinite. So many interesting theories are stably infinite. So equalities with an uninterpreted function, arrays are stably infinite, data types stably infinite. So that's great, these all work. In fact, there's a special case, which is a convex theory. Convex theories are even better. For a convex theory, you don't have to guess any arrangements. It's actually guaranteed that just propagating inequalities is enough to make Nelson-Oppen work. Okay, there aren't that many convex theories, but there are a few. So basically what we do is, as long as our theories are stably infinite, we push all the equalities. If we're convex, we're done. If not, we have to do some additional guessing to agree on an arrangement. Yeah. Yeah. Next one. The theory of bit vectors is not stably infinite. That's because for a particular bit width, there's only a finite number of values that can have that variable can take. So in fact, this is a problem because all of our SMT solvers use bit vectors, right? So I'm not going to tell you about it, but there's actually some very cool work that generalizes the Nelson-Oppen combination method to something called the polite combination method. And a polite theory is the kind of theory that can be combined with any theory. It's so polite, it's very accommodating. Even if you're not stably infinite, it will still work. And it turns out that many of the theories that we care about, including uninterpreted functions and arrays and data types, are in fact polite, which saves us. That means we can still combine them with bit vectors. But the pure Nelson-Oppen method doesn't work, unfortunately. And what do you have to do for polite combination? Well, probably don't need to get. All right, let me try to give you the 5-second version. Basically, what you have to do is you take a formula and you have to create what's called a witness formula. And the witness formula creates some additional terms. It's easiest to understand with an example. Let's say we have arrays and bit vectors, right? And let's say I have an array indexed by bit vectors of size 1, containing bit vectors of size 1. Well, there's actually only 4 such arrays, right? Because each array has 2 elements. Each element can either be 0 or 1. So it's just 2 times 2. There's 4 possible arrays, four possible values for that array. So if I say I have 5 array variables, all of that type, and they're all different, and that's all the constraints I have, then my array solver says, okay, that's good. My bit vector solver didn't see anything, so it says I'm good, and Nelson-Oppen fails. So what I'm going to do in that case is I have this so-called witnessing function that looks and says, oh, if you have a disequality between these arrays, I'm going to need to create a witness, which is an element where those 2 things are different. So it's going to introduce this new formula that says A sub k, A1 sub k is different from A2 sub k at a certain index k. And it turns out just making that, now you're going to get some constraints in the bit vector theory, and the bit vector theory is going to figure out that it's inconsistent. So essentially what you have to do in polite combination is come up with these witness functions and show that they have certain properties, and then everything works out great. Yeah. Not quite, not quite. What we do is we push everything to be equal that we know has to be equal, and then we assume that everything else is disequal. And that's sort of our implicit arrangement that we're working with at any given time. And the theories have to check to see if they're okay with that arrangement. If they're not, then they have to do a k-split to try to find another arrangement that they would be happier with. Yeah.
Is this notion itself stable under union? Is stably infinite stable under disjoint union? Say, for example, if you take 2 theories, maybe it's not. If you take 2 theories that themselves are stably infinite, then is the union of them
Also stably infinite?
Mm-hmm. Because this seems to be a setting where when we're doing these combinations of theories, the reasoning is modulo T1 union T2. So
that's a good question. So I think that's true, but the reason I don't know is because instead of doing that, we have we basically prove the theorem for an arbitrary number of theories. So if you have n stably infinite theories, you can combine them with Nelson-Oppen. So we don't do it one at a time. We just say, give me all your theories, and we have a Nelson-Oppen version for all of them at once. And it is true that that works. So if I give you n theories, they're all stably infinite, then this same algorithm works for that.
Same algorithm.
Yeah. Yeah. And I guess for polite, we actually proved the other thing, which is if I have a polite theory and I combine it, I still, I maintain the property of politeness. So I can sort of combine it with a bunch of things. Yeah. Yeah.
Sorry, I don't understand what an infinite model of T means.
Okay, so I would have to explain model theory to you to really get into the details, but it just means that typically there's a domain for the variables in the theory. That domain has to be infinite. So for integers, for example, there's an infinite number of integers, so you're fine. For bit vectors, there's only a finite number of bit strings of a certain length, so that's why it's not.
So any finite domain theory is obviously not stable.
That's right, yes. Okay. All right, so let's finally look at how do we solve SMT with multiple theories cooperating. Let's see. So what we can do actually is we can extend our calculus to this DPLL T1 to Tn calculus. So let's see how to do that. We're going to fix n to be 2 for simplicity, but it doesn't have to be 2. This works for any n. We're going to index T with this subscript for which theory we're in. C again is the set of shared variables. Right, and then I of m is basically any equality or disequality between shared variables that occur in at least 2 of the sets of constraints. So M sub I means constraints for theory I. And if it occurs in both M1 and M2, then it's a shared variable. So here's how we modify things. When we're doing a decision, we can either decide on a literal, or we can also decide on an interface equality, okay? So this gives us the freedom to make decisions in order to sort of get to that arrangement that we're looking for. Same thing with propagations. So in T propagations, it's not just important to propagate literals that appear in the formula. We also want to propagate any interface equalities or disequalities that we may know. Okay. And then, of course, if you get a conflict, you get a conflict in either of the theory solvers. If your conflict involves, actually, this is just the same. This is just saying that you do conflicts for each theory separately, conflicts and explanations for each theory separately. Yeah.
Okay, sorry, it's a modern technology. Sorry, I'm just confused about this interface equality stuff.
Yeah.
So there could be like, let's say 100 variables. So there's
Yeah.
100 choose 2 that could be equal, right? So that's quite a
Oh,
few.
yeah.
And do you introduce these? I mean, these now become variables because you can decide on them, right? So do you actually introduce them all? Not eagerly, right? Lazily, probably, right?
Yeah, so this is actually something you have to do very carefully. You don't introduce them into the SAT solver at all because there's too many of them. So what you do instead is you handle them with theory propagation. That's the same mechanism as theory propagation. So essentially, if I ever know that basically I'm tracking all the time whether I know if any interface equalities are true or false. If I do, I immediately propagate it. That's great. If I don't know it, then I might need to make a decision. But I only make this decision if I'm not okay with the sort of current default arrangement, which means anything that's not equal is disequal. So the theories have to do some analysis. They have to look at all these. Let's say you've got 100, right? There's 100 shared variables. Maybe 30 of them are equal, right? But now you got 70 of them that are all in their own equivalent. But basically, what you know is an equivalence relation on them, right? If your theory is okay with that equivalence relation, meaning everything in its own equivalence class is different, if there's a model in your theory for that, then you're golden. You don't have to do anything. If there's not a model for your theory, in your theory for that, then you got to sort of say, well, I need some of these equivalence classes to be the same. So let's do a K-split to see if I can find one that's okay. And you have to be you want to be quite clever about how you do that. You want to sort of push yourself towards a model that's good for your theory. But in the worst case, you have to explore a lot of arrangements. Yeah, but this almost never happens in practice. So that's good. Yeah, it's a little bit of a tricky thing. So this calculus, again, it doesn't tell you all of the subtleties going on there, right? But the right thing to do is have every theory basically have a default current arrangement that everybody's looking at. And you try to get everybody to sort of agree on that with a minimum amount of K-splitting. Yep. No, so that's what's interesting. You don't do the K-splitting. Let's see. How do we actually do that? I guess what we do is if the theory's not okay with the current assignment, it pushes out some sort of lemma that's going to it's like the splitting on demand approach. It's going to create some kind of lemma about the splits it cares about, and then the SAT solver will do the splits. Yeah. Yeah, at that point, the variables do get into the SAT solver. Yeah. Okay. What is this? Okay, you can also learn disjunction. Yeah, so you might actually do it this way. You might say, okay, I'm not okay with the current arrangement because I know that like of these 10 variables, some of them have to be equal. So I'd actually generate this lemma that says there are these n interface equalities and one of them has to be true. So I generate that lemma and then the SAT solver would split. Okay, so I think this is my last example. I'll just quickly look at this. So with these rules, I can do something like this. This is the same example, but now in the calculus. Basically, I do these propagations. I do some theory propagation back and forth, and I get the conflict. So this is what the convex case looks like, is basically theory propagations going back and forth with these interface equalities and no splitting. So that's nice. For the non-convex case, it looks like this. We do some theory propagation. Here's where x has to be 1 or 2, but we don't know which one. So we know that x is equal to, so E1 is 1, E2 is 2. So we know that either 11 is true or 12 is true, but we don't know which one. So then we would use this ilearn. So ilearn is like a theory learn, but we're learning a disjunction of interface equalities. So we go ahead and add that disjunction to the formula. Now we can split, try one of them, try 11, propagate conflict, back jump, try the other one, try 13, or sorry. No, we propagate because now we know that it has to be the other case, which is, where do we get 12? Oh, here we propagate, it has to be 12. And then by exercise, yeah, figure out why that's true. Okay. All right, so I think we're out of time, but I have some additional readings if you're interested. Lots of references here. So I'll make these slides available and hope you enjoyed that quick tour of how an SMT solver works.
Question?
Yeah.
So earlier in the morning, we started with saying that all we need to care about, well, let's focus on conjunction of literals. But now we are caring about conjunction of disequalities, which is, if I think from the C, it's like a conjunction of two CNF clauses, right? Like L1 and L2, or L1 and not L2, or L1 and not L1 and L2.
Well, it's still a conjunction of literals. So literals can be atoms or negations of atoms.
But this is conjunction of the disequalities. I mean, these are
Disequalities
disequalities.
are still literals.
Okay, because I thought they are disequalities of the literals, right?
No. The interface equalities are equalities between variables, not between literals. Yeah. So it would be like, I have a literal x is greater than 1, but x is now a shared variable. And I have to know whether x equals E1, which is 1, or x equals E2, which is 2. So the interface equalities are between variables that are in the theory over the domain in the theory. Yeah. Good question. Yeah.
Conjunction of theory. So can we have some constraints which works on both the multiple theories? Let's say like maybe if the value of indifference is less than real numbers.
You're asking if it's okay to have constraints that belong to more than one theory? Nope. So one of the other assumptions that I sort of went through, that I didn't talk about, in order to apply Nelson-Oppen, the symbols in each theory have to be completely disjoint. If you have a shared symbol, then things go haywire. Now, if it's just a naming problem, it's easy. You just rename one of those symbols. But if you really meant for the two theories to share some kind of semantic thing, well, then things get much more complicated. Yeah. No. So in SMT solvers, every theory has its own symbols and they don't share.
There's a common between these theories. Can't you just rename them and add a clause? So for example, I'll add a can't you rename, for example, if the check variable was x, could you just change x to y in one of the theories and add a clause x equals y?
So sorry, I didn't make this clear. Shared variables are fine. Shared operator symbols are not fine. And shared like constant symbols like the number 0 shouldn't mean two different things in two different theories. But variables, we can share variables. That's okay. Yeah.
So the initial structure was very clean, right? So the first few verifications, and you have the new linters. Now the site solver knows that these are my variables and it can work on it. But now with this on-demand propagation of these arrangements, so now the site solver has to be ready for new variables entering the system. So it doesn't cause any side effects or.
Yeah, great question. So in order to make all of this work, your SAT solver has to be also quite polite. It has to be very accommodating, right? So it has to be able to accept new variables and new clauses, and not just you know, at like a good stopping place, like at any point it could just be, you know, flooded. It also has to accept new values for variables, right? The T propagation might just come in and say, hey, you know, Oracle says this variable is true or false. So out of the box, no, the SAT solvers can't do this. So back when I was writing my first solver, I was going in there and hacking the SAT solver to add all this functionality. But these days, we have some very nice SAT solver developers, and they've actually built an entire interface that handles all of these cases. So we can just use their interface. Yeah, it's really nice. Yeah. Yeah, I briefly mentioned it. So it does terminate because there's only a finite number of arrangements. So again, in theory, you can just exhaust all the arrangements and try every one. Yeah. Yeah.
So these combinations of theories, you know, offers one kind of a natural way by which to kind of reason about certain kinds of implications using interpolants. Say, for example, you have theories T1 and T2, and you, as you said, the procedure requires that the vocabularies of the two theories be disjoint. So if you have a formula which kind of is an implication, which is, you know, the form A implies B, but A is on the first theory and B is on the second theory, I mean, classical interpolation results would give you an interpolant in the theory of in the intersection, which in this case is the empty theory, which is just the theory of equality. So do you have, are these results used in this reasoning?
So let's see. So actually, it's not quite the case. The intersection of the two theory symbols will include those shared variables. So the interpolant would probably be something over those shared variables, right? Because the shared variables appear in both theories.
But that's okay for
yeah. So it would be equality and shared variables.
Equality over the shared, right? Mm-hmm.
Yeah. Let me think. So I don't know of any work that tries to explicitly use that fact to somehow accelerate the search for an arrangement. I wonder if it's just sort of equivalent though to the, like this observation may be equivalent, like seen from a different angle to this requirement on the Nelson-Oppen that they agree on an arrangement, but I'm not totally sure.
Mm.
Yeah. Yeah. Sorry, I just can't hear you. Yeah, use the mic so everyone else can hear you too. Here it comes.
So, is there a situation where the theory solver will update one of the variables?
Update one of the variables.
Change the value given earlier.
So the theory solvers don't actually know the values of the variables during this whole process. All they know is some constraints on the variables, right? And what they need to figure out is, do they know if two of these variables are equal? Whether or not, doesn't matter what the values are, just whether they're equal or disequal. Now, when all is done and the theory solver says satisfiable, at that point, we may ask it to give us values. And the values it gives us may not be unique. They may just pick some arbitrary values. So during this whole process, you can't say that the theory knows values for the variables, because it doesn't. Yeah. Is that helpful?
Yeah, so there is no concrete values until the last step.
Yeah, yeah.
Always talking about the communication between various sort of components.
Yeah, so I just had a question. You're always talking about this communication between various kinds of components and the SAT engine and the theory solvers. So in practice, is it the case that they're running in parallel and you're sort of sending messages, or is it everything is like linearized in some sense?
Yeah. So that would be quite a bit more complicated, and I don't think it would buy you anything. So the way that I think about it is the SAT solver is running the show. Basically, it's doing its thing, and then every once in a while, it jumps out and gives the theory solver a chance to do some work. And then it comes back to the SAT solver.
So a lot of the sort of strategy of what rule to apply is implicit in this sort of how you linearize this thing. And when
That's right. That's right. Yeah. I mean, the name of the game is to do everything cheap first, and only in the last resort do the expensive things. So decisions are expensive. Asking the theory solver to check if something really is satisfiable is expensive, and we sort of are lazy about all of that.
Okay.
So yeah, thank you. So I really got a sense of all the science behind SMT solving. So thank you for that. But I think I'm missing the engineering piece a little bit. You know, there are a lot of kind of questions here about, you know, which theory solver, how much to learn, whether the interface variables, how much to learn there, etc. I mean, it would be great if, you know, there was some, you know, if you would be able to say something about that, like where is the maximum bang for the buck, where the optimization heuristics work best, and what are the next kind of frontiers to
Yeah.
kind of tackle?
Yeah, I mean, we really need to write a book because you just asked like 4 questions that are answered in like 10 different papers, right? So, you know, how do you optimize this search for an arrangement? So we have a whole series of papers on polite combination, on creating what we call a care graph, which tells you which part of the arrangement you have to explore and which ones you can ignore, things like that. How does each theory solver work? I mean, mostly we've written like complete journal papers for each theory solver. And, you know, for each theory solver, we have a calculus. We prove that it's sound, complete, maybe terminating, not always, depends on the theory. Some of them are, we don't know if they're even decidable. So we like give as much guarantees as you can and show how it works. And then there's all kinds of optimization. So just to give you an example, in the theory of strings, we wrote a first paper about this theory back in 2014 and gave a calculus for it. When we found out Amazon was using it in Zelkova, we said, oh, can we help you? And they said, yes. We got all these problems that aren't getting solved. We wrote like 5 more papers on how to optimize that theory by doing special kinds of rewrites, by doing a special calculus for rewrite rules, all this stuff. So, I mean, it's a vast subject. There's a lot going on. And even if you read all those papers, right, you have to read the code to really know what's going on, right? And it's 300,000 lines of code. So, you know, if you really want to understand this stuff, then I invite you to do a PhD on SMT solving. It's a really fascinating area. But yeah, there's a lot that I just didn't have time to cover. The idea here is just to give you a big overview of how all the pieces fit together, so that you understand at least what are the pieces that you would have to build. But then building each of those pieces isn't, you know, there's a lot more that goes on. Yeah, of course. All right, maybe that's a good place to stop. Thanks.
Half an hour, but please try to install CVC 5.
Yeah, so if you haven't done it already, I would say that during the break, please try to do the installation instructions. And then we'll talk more about what to do after that. And if anyone's having trouble installing it, let me know, I can help. think the Okay, so some of you have asked me about my work in automated reasoning and bringing that together with AI. So I asked SuperTick, and we're going to do a bonus lecture on the last day, the last session. So if you were thinking of skipping out early, don't do it because you'll miss out. All right, so this is just a teaser for the lecture I'll give on the last day. Okay, but what we're going to do right now is this SMT solver lab. So has everyone managed to install CVC5 according to the instructions here? If you haven't, I can come help you in a minute. But so what is this lab about? Basically, we're going to build a simple solver for integer difference logic. And this is the algorithm that I went through in the lecture, where we first do some rewriting, and then we convert to a graph, and then we check for negative cycles. So if you try to run the code that you've built on one of these examples, so let's say you try this example right here, you'll get expected result unsat, but got sat. And the reason is that the code I've given you, it builds the graph, but it does not check the graph for a negative cycle. So there's like a little comment in the code that says to do, and you have to implement that part. Now, if you implement that, you'll get another problem right here if you run this other example, because the other thing that's not implemented are all of those rewrites that I told you about, where you have to turn everything into less than or equal to. So let me show you the skeleton code here. And you can see, so the skeleton code is in this CVC5 source theory arith IDL extension.cpp. And if you search for to do, all caps, TODO, you'll see this. So let me just walk you through a little bit of this, and then I'll leave it to you to figure out what to do. Sure. Is that better? Let's see, can I close this? Yeah, here we go. All right, so there's this function in here called PP static rewrite. PP stands for pre-processing. So during pre-processing, once you've parsed the formula, it's going to go through and it's going to call each theory to see if the theory has any specific processing that it wants to do at pre-processing time. And here's where we're going to rewrite everything into less than or equal to. Now, you can probably figure this out, but basically a node is a formula, okay? And we're going to, so if we, whoops. And a T node is essentially the same thing. Don't worry about it. This atom coming in is essentially the thing you have to rewrite. So first we're going to say if it's not a Boolean return, we're only going to rewrite atoms. We don't care about anything that's not an atom. This is kind of useful. So we have this general mechanism in CVC5 where you can say trace, put something in quotes, and then print anything you want to that. And then if you run it with -t and the thing in quotes, it'll actually execute these, but if you don't, it won't. So this is a general tracing mechanism for figuring out what's going on. Here we're going to say, all right, so this is a little bit tricky. Let me tell you the structure of this code. What can happen is I might have x minus y equals 5, but I might also have 5 equals x minus y. And I don't want both. I just want one. So this is going to say if the left-hand side, so 0 means get the 0th child of this expression, and all of the atoms in integer difference logic have 2 children. So it's either A equals B, or A less than B, or A greater than B, whatever. So this means get the left child and check what kind of a thing it is. If it's an constant integer, that means I have 5 equals x minus y instead of x minus y equals 5. And so what we're going to do is we're going to switch it to the other, move the constant value to the right-hand side. We might also have the case where we have x equals y, okay, which is the same thing as x minus y equals 0. So we want to turn that into the form that looks like everything else. So down here, we actually have the usual case where we have x minus y operator constant. So we've done one case for you. What if it's an equality? So if I have x minus y equals constant, then what am I going to do? Well, this shows you the kinds of things you can do, right? So I'm going to make a new node, which is a less than or equal to from the left and the right child of the current node. Then I'm going to check that the left-hand side is actually a subtraction. It should be if we're in integer difference logic. Then I'm going to negate that by taking the right child of the left child and subtracting it from the left child of the left child. So I had x minus y, I'm switching it to y minus x. Then I go ahead and get the value of the constant. That's what this thing does. I make a new constant that's the negation of that. Create the less than or equal going from the negated left, less than or equal to the negated right, and ultimately create the and of those two things, okay? So this code is doing that first rewrite I showed you, where if I have x minus y equals c, I turn it into x minus y less than or equal to c, and y minus x less than or equal to minus c. So that one is actually the most complicated one you have to do. So you should be able to figure out how to do these other cases. All right, so that's the rewrites. And then further down here, we've got this negative cycle. So what's happening is we've put all of the graph into this thing called D underscore matrix. And your job here is to check whether D underscore matrix has a negative cycle. Now, one thing you might want to use is this nice function called print matrix, which will actually show you what the graph is that you've read in. All right, so you could put a call to print matrix here and see what the matrix is for that simple example. Yeah. Yes. No, it contains weights, so it contains rational values. No, so there's also a valid matrix. So valid is telling you whether there's anything there, and if there is, then you get a value. Yeah. Okay. All right. So I think hopefully the rest is kind of self-explanatory, but maybe as a hint, the first thing to do is run it on that first example, the example rewritten, and go in and add a call to print matrix in that negative cycle function to get started. And then you can start thinking about, well, how do you detect that negative cycle and how do you solve that problem? Okay, so there are several challenges. I've made it so hard that no one can possibly finish it. So your first challenge is to do the negative cycle. All right, so you can, implement Floyd-Warshall or find your own favorite negative cycle detection algorithm. Then your second challenge is to complete the to-dos in the rewrite. Oh, this should say static rewrite. And then if you get that done, the last challenge is to see if you can actually generate models. So there's another to-do that if you ask it for a model, it should give you back values for each of the variables. All right. So I think go ahead and read through this documentation and see if you can figure it out. And I'll be around if you want to ask questions. Okay, so I think we're at time, and I don't want to keep you over. So I hope you enjoyed the exercise, and feel free to keep working on it throughout the week. I'll be here if you have questions. If you're feeling extremely motivated and you got through everything in the lab, now you can try your hand to see if you can beat the CVC5 native algorithm. So the native algorithm in CVC5 does not do anything special for difference logic, but it is optimized for SMT, whereas the algorithm you implemented is not. So you could try it on some harder problems. You could try it on some SMT lib problems and see what you get. So if you can beat the native CVC5, I don't know, and then you should get a prize or something. So, all right, but thank you very much. I hope you enjoyed it, and I hope to talk to you more the rest of the week.
Have one more talk by him. So